Happy to welcome you back on our last fifth day of multi-GPU AI Train the Trainer workshop, which has been ongoing from 30th of January until today, 5th of February. We are starting as always from morning 9:30 until 5:30 p.m. with a lunch break between 1 and 2 p.m. and additional coffee breaks if needed. I'm happy to say that from our side of in a backside of all this organization is coming from Project CASTIEL 2, EuroCC2, Sineca, and Barcelona Supercomputing Center. And thank you very much for participating in this all 5 days with us. Today, for our morning session, we have a trainer, a speaker, Michele Visciarelli from NCC Italy, and he will be talking about the Ray Plus Retrieval Augmented generation. And in the afternoon, we are having a speaker, a trainer from NCC Finland, Oskar Taubert, and he will be speaking about hyperparameter tuning. Thank you again, everyone, for being here, and we hope that you enjoy this learning and training with us. And I'm happily giving the floor and the microphone to Michele. Thank you.
Thank you, Vasa. Thanks for the introduction. So I'm Michele. I work at Sineca in Italy, and I'm a data scientist, HPC engineer, and so on and so forth, basically. And today we are going to talk about two things, a little bit separate, but it could be interesting both. First, up until the first break, it's going to be Ray, which is a parallelization tool of course, parallelize workloads. And then we do a little bit of a retrieval augmented generation from scratch. So we're trying to build up what it is and how to make it a little bit more efficient. This second part is a little bit more application of LLMs. So it's not strictly just, HPC or parallelization, but of course, the models that are going to be used need parallel resources because usually are larger models, the LLMs basically. So let's jump right in. I'll share my screen and I'll basically give you some way to run everything today. Basically, I suggest you to do a git pull of the course repo, and everything should be up to date there. It's going to be something like this. Here I just have the two courses for today, but you will probably see also the original Leonardo one. Here it's in the IT part, Italian, let's say, part of the repo. And everything today is going to be inside notebooks. There's no slides in there, but there's a lot of stuff that we're going to read and explain. So let's say, don't worry about this. There's everything in there. And I'll just go straight in. I suppose that you're probably able to access at least the folder, which is the intro to Ray, the start. The environment has been already prepared. So the only thing that you need to do is basically launch this script. It's called Start Ray Interactive, which I'll just go into it a little bit in detail just to give you an idea of what's happening behind the scene. Here are the usual SBatch comments. I prepared an environment for all of you to use. And here, basically, we are just launching Ray together with a Jupyter notebook in order to have it basically connected to the Ray server. And simply, just to make this extremely quick, SBatch start rayinteractive.sh should start in a second. We can check Yes, it's starting. There's already the reservation there. I already basically prepared everything for you, so there's nothing that you have to change. And here we should probably see, as soon as you launch it, these two files, the .r and .out. Now we have to set up the tunnel in order to open the Jupyter Notebook. So let's just go right in. You would probably see something like Array Web UI and Jupyter Server. This is the one that we are interested in. Let's just copy. And then on your local machine, sorry, whatever it is, here, just paste. Now the tunnel should work. And going back to this file, open link, and we should be in. So please let me know. And yes, let's wait another minute, and then I think we can go. And I think I'm going to start. This first part is a little bit descriptive, let's say. And we're going to talk about Ray in this first part. And we'll try to introduce, first of all, the main Ray concepts. So basically, why would you want to use Ray? So, which is a parallelization library. What do you want to solve with this? So basically, I mean, when you have a Python program and becomes slow, often it's because you have many independent pieces of work that could run at the same time, right? Like per user requests, I don't know, batch modeling, etc. And of course, one single machine can do so much in parallel, and a cluster can do much more. And Raycore gives you basically very simple programming model for this. So basically, you run a normal Python program, which is the driver in a certain sense. You basically hand out the work to array cluster as tasks, which are at the stateless function. Ray then, the cluster turns those tasks across many processes or machines or whatever, and gives you back the handles to the results. And this is object refs, so we'll go to this into detail. And then you pull the results when you actually need them. And everything else is just purely infrastructure. So Ray, it gives you all of this. And regarding the Ray cluster, it's very simple in a certain sense, which is just one head node and 0 or more worker nodes. And conceptually, what is happening is that your program, which is the driver, it connects to the cluster and then submits work, basically. The cluster is then responsible for executing that works somewhere. The difference between head node and worker node is that the head node runs cluster management services, most importantly, which is the one that is the global control service, in addition to the normal worker components. Ray can schedule tasks on the head node too, but of course, in larger cluster, you may want to often avoid this and have just one dedicated node for this. In our case, and this is a kind of a toy example, we are running also in the head node, in the single head node. We have, we will see that we will have some resources at our disposal, mostly CPUs and one GPU, and we will use them. And Again, the main components that you mostly want to be aware of are basically four. Again, the driver, which is just your Python process. In this case, it's the code that is in the notebook and submits tasks to the results. Then you have the schedulers, which basically respond to where should I run the stuff? And Ray decides which node should run each task using the resource availability and load balance techniques. Then you have the workers, which are the actual Python processes that execute the remote functions. And then also you have this other thing, which is the object store, which basically is where the results live. So when a task returns a value, Ray puts it into let's say distributed shared memory object store, which is one object store per node, basically. And what the driver receives is an object reference of this, not the full value. You need to use a specific call to actually get the full value. And I think having this analogy could be helpful for you. So, it's like I don't know, a serving kitchen, something like that. It's the driver, it's placing orders, right? Then the scheduler, it's like the kitchen expeditors, basically, it's decide which station cooks what, or something like that. The workers are actually the line cooks, and the object store, it's the tray when all the plates gets put until someone picks them. So this is the idea, basically, of Ray. So let's start actually going right into this and connecting to a cluster. So, I mean, you could run all the cells, no worries. I've pre-ran them, so I think it's just easier for me to follow, but you can just go and try yourself and doing everything. So you will see what is happening. And here it's just, there's just a simple library. It's Ray. Everything that you would need, it's inside this Ray library. And then a little bit of something else for later demonstration. With the job script that I showed you previously, I'm just going back into it for a second. You will see, especially here, yes, this part. Here we started array cluster. You need to, in order to do this, you need to create an environment with Ray and then run this code, because this starts a cluster at a certain, node address, and it associates a port to it. Then when you have this, inside your notebook, it's simple notebook, you can get something like this, basically, something very simple. The first thing that you will notice is that we have exported the array address in our bash script, so it knows exactly where to connect. But basically, when you call ray.init, which is the initializer of the connection to the cluster, Ray, even if you don't explicitly state an address, Ray tries to find an existing cluster using the Ray address variable first, then an explicit address parameter, or search for locally started Ray instances, as this is the case. But to make sure, we define an array address in our in our script. Then if you run this cell, I'll run it too, why not? Because this is very simple. It takes a while to run, but it should be okay. Let's double check. In the end, you will see this part. Our clusters have a certain amount of resources, right? As you can see here. The what we will see, since we have defined this type of cluster resources, is that we will have 8 CPUs, 1 GPU, and some memory, which is divided in execution memory and object store memory. So this is kind of crucial, this definition, this differentiation between execution and object store memory. So the execution memory, it's the normal RAM memory that it's, let's say, used by a Python process. While the object store memory, it's the shared memory used to basically hold all the array objects and results while they are processed and before they are called back. So usually when you don't set up anything here in the cluster, you are basically saying that you are dividing the resources in 730 different, in 730%. So there's 70%, which is the execution memory, and 30%, which is the execution memory. Then let's try some example. Very easy. So let's define a simple function here. This function simulates a database in some sense, in which you do some kind of very long operation. So basically, in this case, it sleeps for 2 seconds and then gives you some names and returns a simple string in which it says that the data was successfully loaded. And this just simulates it. And when you're going to run this, you will see that every 2 seconds, you will have this different strings that are recorded here. And it takes 10 seconds. And this is what we expect. This is a serial, let's say it's a serial type of execution. And there's just one single worker, which is my Python process here, that is doing one thing at a time, basically. And as you can imagine, this is parallelizable. You can imagine that every operation on a database is completely independent. And you can decide, okay, let's try to do this in parallel. And this is where the array task basically comes into play. The only thing that makes the only thing that you need to change is introducing this decorator, array.remote. It's very simple, as this. You just add to your original function this decorator, array remote, and this becomes automatically array task, which is by definition a Python function with this array remote decorator. And what will happen here is that if we do the same thing as previously, like try to run this, you will see that we don't have exactly the output, this string here. We have an object ref, because this, as I was trying to explain previously, these array tasks work inside the object ref memory, and everything that is produced stays there up until you explicitly ask for calling it back. Think of it, think the object ref as sort of sense a claim ticket that the results that will exist later in some form. So it's stored there, but it doesn't print anything. And you also have to do this other interesting thing. Previously, we were just, let's say, printing the function directly. Here, since this is a remote function, so a task, in order to invoke it and call it, we need to use the .remote name, and then it will return this object ref. In this case, you will probably see that the execution time is much more faster than previously, because this is basically asynchronous submission in a certain sense. So what happens here is that with this addition, basically, Ray can run this function on different CPUs at the same time, and so work in parallel, basically. In this case, since our cluster has more than 5 available CPUs for those tasks, these 5 sleeps can overlap, and the wall time in general that approaches 2 seconds here. It is just for the execution on one of this toy function at a time. And what is the, let's say, the scheduler doing at the high level? Basically, the strategy for the Ray scheduler, the default strategy, is trying to balancing let's say the locality. So trying to run on already prepared nodes, balance the load, just one task for one CPU for one worker, and trying to meet resources constraint. You don't really need to micromanage the placement of the tasks inside the workers. This is done by Ray. You are going to define just, and we will see this in future, how much resources do you want for each Ray task. Now you can think of, okay, there's everything, right, inside the object store, but how do I get this back? So basically, how do I redeem the ticket that I basically sent previously, that I got previously? And you will need to use this ray.get function. So basically, this ray.get, it's getting the references, these refs here. Basically, ray.get blocks until the object is ready, and then it returns the real Python value. This is basically a synchronizing point here, you will see. In this case, you first you define a series of remote function here inside a list for naming names. We have 5 names, right? So here I'm placing all my function in remote and running them. Then what happens is that with ray.wait, I run all of them in parallel, and I just wait for each one of them to finish. Then I have the references, which is the finished, and I get one of them at a time, but in parallel, basically. And ray.wait, what it returns in this case, the ready refs here, and the unready, the ready refs here, and the unready refs, of course, to print them in the quickest way. You want to access the finished one. And in the end, what happens is that basically it takes 4 seconds in order to do all of this. Just to make everything clear, what does this loop basically does? It waits for at least one task to complete with this ray wait, pulls its value from basically from the object store with ray get, and repeat this until none remains. And this is basically a pattern that you may think and keep in mind to be responsive pipelines. Basically, it shows progress. It starts downstream immediately as soon as you have the first result, and avoid, let's say, waiting for slowest tasks, of course, because you can imagine that some of these tasks, if this is actually, I don't know, a database operation, it's not exactly 2 seconds for each one of them. Maybe some of them finish early, some later, but as soon as you have a result, you can basically print it out. And now, before starting with ray actors, I think the map that you would probably want to keep in this case is that, in general, submit work tends to be cheap. With ray.remote, it returns immediately, so it's really fast. The results live in the object store, because you just hold this object ref until you choose to quote unquote materialize it, and then you exactly control when you want your block back, with ray get, with ray wait, and so on and so forth. This is the, let's say, very core of the ray tasks. But you may ask yourself, now let's suppose that we want to keep track of the number of the, let's say, all of this, the number of times that the user logs inside to our website or whatever it is, or database. So now we can think about this. We can use these ray actors because we have a problem with the ray tasks. They are stateless. So let's suppose that I need memory or I need a state that I want to keep. Ray tasks are pure function calls. So you basically, let's say, call them. They run somewhere in my cluster. They return a result, and then they don't remember anything between the calls. There's no state. For example, using the previous example, how many times has Michele actually logged in daily? I want to keep a cache for, I don't know, load the profiles, or maybe for more complex application, there's an LLM that I want to load. And as we know, these are big objects, and I don't want to do this all the time, but I just want to do this once and keep them. And this is exactly what ray actors do. These are, let's say, stateful objects that let us keep the information. They are always defined as a Python class, which it runs on its own worker process, and it has some instance variable, self dot whatever, that persist basically across calls. This is the most important part. You basically also call these methods remotely. So this is the interesting part. And so let's conceptually look at this. This is a fake database that we just want to keep track of the accesses. As you can see, it's very simple. Again, it simulates a very long operation on the database, and it just keeps track of the number of accesses that a user have done. Also some other information regarding server ID, etc. And then it should return the number of accesses. Then we create the one instance of this class. And again, it's remote. In this case, we have to define this DB backend. We can change it, it's MongoDB, whatever. And then what we will do is, again, launch this, we can launch the task on the actor. So as you see here, there's just a slight difference. Here we are, before it was just this part, right? Because we had just a ray task. Now we submit directly the actors in our cluster, and we call their methods. Again, if we print the refs, there's just object IDs. And we can do, again, the loop that we tried beforehand. This is interesting because what happens here is that the wall time for this execution of this toy example is actually 11 seconds. So there should be something going on here, right? And what happens is that in this case, it's one single actor processes method calls in a queue. So what happened here is that we used a single actor, but we remotely placed the different method, the same method of the same actor, right? But since it's just one actor, it's executing them sequentially. So we don't have any speed up in that case. So even if our cluster, it's 8 CPUs, what happens is that we have one actor, so one, let's say, service instance. All the incoming method calls kind of line up one after the other, and it runs them one at a time. Again, this you can think again with another analogy that I try to formulate. The tasks are like send this specific task to, I don't know, a huge call center or something like that, and a single actor, it's like send everything on a specific operator, right? So what happens here is that you are overloading your operator, and you get a queue. Now let's try to see how we can actually use this in a parallel way. And since we have like we have 8 CPUs in this small cluster, we can benefit from multiple actors, when you need state. So instead of just one state database, we may create I don't know 5 of them in this case, since we have 5 users that we expect to poll this DB. And so we create these 5 actors, and then we route requests to different actors. And then we basically call different actors in parallel. And in what it happens here exactly is that we need to use this actor pool, which is let's say a method that comes with the library. And as you can see here, we are directly spawning many instances, remote instances of the fake DB, with the definition of its parameters, etc. And then when we want to actually execute in parallel, we map each actor to a specific value. So in this case, the actor pool that we defined, we map it with a lambda function with actor and value. And then the actor is just what we used to do previously. So load people data remote with the values and the names. And then we can print the list of these mapped jobs, and we actually get everything that we want. So this is a way to parallelize your tasks, your whatever instruction that you want to parallelize, and actually persist information on your state. And so again, with the cluster that we have, just to give you an idea of what happens under the hood, each actor effectively is consuming just one CPU worth of scheduling capacity, basically. We can keep several of them running at the same time, concurrently. Then we have 5 logins that last 2 seconds or something, can actually approach the 2-second spread, 2-second time, because they are spread around multiple actors. It's a little bit more because you have a little bit of overhead of communication, but this is the way that basically persists state. So again, rule of thumb: if you need state in your application, use actors. And if you need throughput, so you want to do a lot of stuff with these actors, don't funnel everything through as just one actor, but use multiple of them, unless you specifically want each single actor to do some serial operation. So imagine this fake DB logs the access, but then does something else, I don't know, loads some data, changes some data, and stores some data. The better way to parallelize this is spawning many different actors, each one of them doing some serial operation, sequential operation on the data that it wants to do. And then this is correctly parallelized. Now let's move to the object storage. There's no other question. I think we can go back to the object storage. So this is the distributed object storage, basically. Again, as I was saying, it's the 30% of memory of a worker. And the object store keeps the task results, the actor method results that are there, and the objects that I want to explicitly put there. And in our case, it has 30% of the memory of our job, which is around, in our case, 160 giga. So it's a lot, but that's the what we have available. And again, I want to stress this. This is not normal Python RAM. It's kind of a dedicated pool used to hold array objects in there, so they can be shared, efficiently across the different nodes, right? And the other thing that you should probably remember is that if, for whatever reason, it spills to disk, which is much slower, as you can imagine, and then this reduces the performances of your your program. So there's two methods that are really important to understand, which is rate put and rate get. So as a very simple example, let's say that we have, in this case, it's really toy example. We have this string or whatever, an API key, and I want to put it in the object store memory. So it can be referenced by many different, entities or whatever. In this case, I do rate put, and it's going to be inside the object reference storage, and you will have the object ref. And again, if I do rate get and I use the key reference, then I get exactly this the key. So to come back also, now that I think a little bit more to the question beforehand, one way to make the results of a certain actor be seen by another actor downstream could be using this rate put. Of course, if it's not a huge pile of data that's going to clog the object ref memory. If you store somehow the object ref, then with get you can get them again and start a second actor with the reusable part of the previous actor. But again, it needs to be let's say you really need to focus on how much memory I'm going to use, and if I can really do this in terms of capacity, latency, and so on and so forth. So sometimes it may be beneficial, but sometimes also not. It really depends on the application. But just to familiarize with this, let's try again to look at this, let's say, toy example. And in this case, as you can see here, this is kind of an API helper, whatever. It gets an API key, and then you get the endpoint. In this case, random, whatever. It's just an example. Remember that we put the key reference inside the object reference, object memory, sorry. And then here I can quickly define my API helper, right? Remote. So again, it lives as a worker, inside a worker, and give the key reference simply as this. If I do a rate get of the call endpoint, again, .remote, because I want to have, I want to run everything, then I can actually get a printout of the API key that I sent in input. So this is the what happens under the hood in this case is that basically you pass key ref as an object ref into API helper remote here. And then Ray automatically resolves the dependencies because it fetches the object value, the underlying object value, and then provides it to the actor constructor. And then basically Ray behaves as it did a certain ray.get for the remote side, right? At the right time on the right node. So this is really powerful because you can, if you think about it, you can basically write distributed code without constantly micromanaging, let's say, all the different data movements. And then automatically Ray builds the kind of a dependency graph. So this actor can't initialize until the object exists, and so on and so forth. So it gives you basically a lot of, it gives you a lot under the hood automatically. And now kind of we have the base picture. We define the array tasks, the actors. We know about the object ref, how it's how they work and how they are powerful in a certain sense. But up to now, we let Ray decide the resources, and it's something that we usually don't want. We want to, we want to use specific resources, specific part of memory, and so on and so forth. And so you need to kind of remember that Ray, at the very core, is a scheduler. And to schedule correctly, it kind of needs to know what a piece of work to do, requires in terms of resources. And it is very simple to do because we already introduced Ray remote, right? But inside this, you can define the number of CPUs and the memory that you want to use, and also the number of GPUs that you want to use. If you run this cell on your on Leonardo, on your local machine or whatever, you will say that even if the number of CPUs is 2, the task sees 8 CPUs. This is another interesting thing. So here for this, we basically scheduled only 2 resources for this task. And we defined basically around 500 megabytes for this logical memory for this task. But you need to remember that resources are kind of logical in the sense that the number of CPU cores or GPUs specified are not really kind of enforced by Ray. So in a certain sense, if you request number of CPUs equals 2, the Ray the Ray server would schedule fewer of them in parallel, which is pretty good, right? But inside the task, kind of nothing prevents your code for using more CPU threads if you kind of do something wrong, or if kind of another library spawns other threads inside your task. And it's kind of the same for GPU memory. So it's really easy to mess this up in a certain sense. Ray can prevent, in a certain sense, too many CPU tasks to be scheduled in parallel, right? But it cannot really enforce, GPU memory usage or CPU or RAM usage, etc. You can still, of course, out of memory if you called allocates too much in a certain sense. So what happens here is that you are saying to this task to use up to reserve 2 CPUs. But if for some reason it overflows, it just doesn't run, and it just doesn't work, and we stop execution basically. So just for a small, let's say, food of thought, again, we will give you some exercises. So let's try to think what happens if you set the number of GPUs this high, right? And in the previous example task. And what happens if you say number of CPUs, number 5, in the task load people data in the previous one. So just to give you an idea what happens is that in this case, you will still go to serial execution. Because of course, each one of the tasks, now we reserve 5 CPUs, you have 8 CPUs, so the remaining available ones are just 3. And since each task should have 5 CPUs, there's just room for 1. And here it doesn't work because there's no room for this because we just have 1 CPU. So it's just not going to run. Just to give you an idea, you always need to remember all of this. Now we can continue with something a little bit more practical, in a certain sense. And now let's talk about this embedding part. It's another toy example, but it's kind of real-ish, workload pattern in a certain sense. Let's say that we have many files, and I want to embed each file. The model initialization is expensive, and I want to parallelize all of this. And here it's very simple. And now we define an actor for this. In here, you see that we instantiate the sentence transformer. Here it's in this location. If you want to try it yourself, it should take a few seconds. And then we just read a certain data file, which is a canto of the Divine Comedy, just again as a toy example. We want to extract the number of this canto and then calculate the embeddings and return a dictionary of the embeddings of this text, basically. Why we use an actor and not a task? Because the sentence transformer is quite expensive. And we want to initialize, we want to load it just once, right? And reuse it for many files. So this is a situation in which we will have just one actor. In this case, it's just one actor that will have some function call in parallel, as you will see. So now the Ray remote here, what happens here? We have at our disposal in this small cluster one GPU. So this will tell the tells Ray basically that each embedder actor should consume up to 0.05 GPU quote unquote tokens, so parts of the memory. And what happens is that if we stick to this, you can see that we can stick like 20 embedders at once in a single GPU in this case. Regarding CPUs, basically it tells this is not important in this case. Everything works on GPUs here. And if we go after the file loading, as you can see here, is very simple. Now we can think, okay, let's try to instantiate 20 actors all at the same time. Always check the number of actors you schedule that they fit actually in the available GPU memory. We made sure of that. We know that it's a very small embedder, so it fits in this part of the GPU that we want. So we can schedule 20 of them. We reserve our space. We put everything, and then we do the thing that we basically saw previously. We have the actor pool. We do the map with the actor and the caller function. We put it remote, right? And then we just, run everything, and we see that it's actually extremely fast. For if you think about it, we have around more than 100 of this Canti, if I remember correctly, and it just takes 33 seconds because it's massively parallel. So.
Sorry for interrupting once again.
Yeah, sure,
I have a question about when you specify actor resources required. You said not 0.05, and sometimes when we have access to a better infrastructure, for example, 800 GPU instead of a consumer one, we know exactly that we can actually use a different fraction of the GPU. And I was wondering if we can some kind of dynamically define this decorator ray.remote or adjust it so that we know that when we run it in an environment with more capable GPUs that we can actually tweak it.
So to my knowledge, no. I think you have to hard set it somehow in the ray actor. But I think you can kind of circumvent it in some clever way, in a sense that if you know that a task is maybe if you have a part of your pipeline that is going to use fewer resources and then another part that's going to use much more resources, you can try to divide the actors in two, save everything in object store, and then start again from what you put in object store with ray get, and use a larger resources allocation. I think this is the one thing that you could do. I honestly don't know if you can dynamically allocate resources. I never had the let's say the necessity to do this. This is yeah. There's always some part that probably I gloss over as a student, which is in order to massively parallelize everything, you kind of need to have a really strong knowledge of what you're going to use, and then how is your data in a certain sense, because of course you want to maximize the throughput of everything, you know, risk fewer crashes as possible, and usually do a lot of, you know, test runs before the really large, extremely parallel run that it's going to, you know, in the end, you know, manage all your data or run whatever you want. All right. So let's proceed, basically. We were here at this point, instantiating the actors. And then we just, you know, map everything here, do the mapping. So for each file path, the actor pool picks an idle embedded actor, and it calls the actor remotely, right? And then it yields the results as they become available. This is basically what it does. Again, 20 of these actor pools, right? Then I call this remote, right? And each one of them gets called by the scheduler to run this call function, it's called method, sorry, as soon as it becomes available. So everything is, you know, always occupied in a certain sense. And the interesting thing here to note, again, always remembering the fact that everything is an object store, etc., is that the embeddings here it's not a finalized list yet. It's, again, an iterator object here, basically. So if you want to really see all of them, you have to do this list of the embeddings. The actor pool returns always an iterator, so you have to kind of materialize it in a certain sense. And in this case, we materialize it with this list embeddings, which takes time. This is the actual operation that gathers everything, 33 seconds. And then we can just see that we have all the embeddings in this nice data frame up to 767, which is the dimension of the embedding dimension of the system. So this is basically the Ray core part, the most basic one. Remember, if you're running this, to run also Ray shutdown, because we, you know, give up the resources, and we can actually go to the second one. I'll try to be quicker than than I was before, which is the Ray data part. Ray comes with 4 different components, which is the Ray core that you just see, the Ray data here. Then there's also Ray train and Ray tune. Probably we won't have time to look into Ray train and Ray tune today because time is quite short. But I provided you with notebooks with all the explanation that we need, an example already pre-ran, so you will see everything. So if you want to implement this, try them in your own cluster, etc., you could. So you will have all the information at the end of this, this part of the lesson, basically. So again, let's talk about Ray data. As you can imagine, it is about a distributed data frame like a structure. So Ray core gives you the distributed runtime, the processes, the workers, the scheduling, the resources, the object store, task connection, and so on and so forth. Ray data instead gives you a distributed data frame like abstraction, which is called a data set, because everything is called a data set, basically. And it usually represents a large chunk, a large collection of rows of your data, which stick with rows in this tabular data in this case. It's going to split everything into blocks called chunks, and each block can be processed kind of independently, in parallel, on different workers. And again, we introduced like the cooking analogy previously. I wrote it down something because it's always, I think, really useful to understand. Basically, you write execution plan for what is going to happen. For example, like this one. Here you are writing kind of an execution plan, right? And nothing until runs until you forces execution, which is the materialize. So again, it's like a recipe up until here, and there's the actual cooking part, right? So let's go back a little bit and look at all of this. Of course, I forgot to say why it's important in HPC, this one, because if I have data which is in, if it's kind of, if they are in slower chunks of memory of your storage, parallel read might become, much more faster in order also to gather up all the data that you want. Also, another thing that I forgot to say, array dataset, it's not a pandas data frame. I know that the terminology is not the best one. It's kind of a distributed collection. The blocks are spread across different workers and the nodes. And you should assume that usually you can't print the whole thing in the driver notebook because it's a costly operation. This notebook here that you see, it's the driver again, and the heavy lifting is always done by the worker processes. So nothing new here, a bunch of imports. We also import pandas because we will see something. We have the environment configuration. Again, it's the same thing as previously. Again, pre-ran because it becomes easier to follow, but you can run it just cell after cell if you want. So you see the thing happening in real time. And we have the same resources because the cluster is the same as the previous one, for which we have released resources. Now, let's go to the actual interesting part. This RAY dataset. So first of all, RAY data supports ingestion from many different sources: CSV, Parquet, JSON, local, cloud. You can do whatever you want. And reading can, of course, in general be sped up if you have stuff on fast storage, as is the case here. And of course, letting RAY parallelize everything. The block concept. So every dataset, RAY dataset, it's split into blocks. Blocks are chunks of rows. The RAY schedules this operation blockwise. So if I have n blocks and a certain number of CPUs, let's say C or whatever, up to around C blocks can be processed simultaneously. The others are kept in queue. Here, very simply, what happens here is that I have this data in this folder, which is open, so you can use it for this course. And here we do some stuff. We read the CSV, okay, and then we do the plan. So we limit the reading to 1 million rows, right? And then we repartition everything into in a certain number of CPUs. In our case, in 8 CPUs. So blocks, these blocks here are the units of the RAY data processes. And this is a reasonable first approximation. So we try to use everything. We divide our million rows up to 8 because we have 8 CPUs. And, we do this in a massively parallel way. Of course, this is something that you want to tune in your application. And this dot materialize, this method here, it's actually the key execution trigger for this cell, because it means that actually execute the plan up to this point and store the resulting blocks. So what happens here is that it runs this. The resulting database blocks, dataset blocks are computed and pinned, so later operation don't reread or compute everything. And then we can access the data frame. As you can see here, this is the operation. You will probably see something like this. It should be really fast, that works, etc. Different tasks that work. And in the end, you will see, if I just do df. I don't have the pandas data frame, but I have these materialized data sets, which you have information. That explains the number of blocks, rows, the schema, and so on and so forth. This is and all the information that you would need. So now let's look a little bit more in the API, because again, you don't want to materialize all the time. You just want to do operations, so do all of this recipe basically. Let's see. How can I say this? Basically, what we can do here is that there are many different important operations that we could apply that are the basics of everything that we want to basically do with our database, with our data frame. And some of this trigger data reading and execution. So for example, here, in this case, take batch or write CSV are operations that gather everything or a batch and do something and force the execution of the plan. In general, you must think of operations that you can do in two large categories. The first one is the transformation, which are lazy and just build the plan, which usually it's map batches, filter, add column, repartition, random shuffle, and so on and so forth. And then there are the others, which are the actions, which is, I don't know, a take call, a take batch, a count, a show, a write in some sort. And these are operations, again, do something. So in this case, we can continue, basically, and see some of these operations, which is very trivial. Again, these they really don't do anything, but count does. It actually gets everything. But here you can do some operation very, very simply. Columns, it's just return the columns names. Again, if the scheme is already known, this is usually cheap. Count returns the number of row. And this forces a scan, an action, so it materializes it. Size in bytes and number of blocks, again, a trivial, it's the size of the GB and in GB and the number of blocks. And now we can actually look at our data frame. As we were saying, you should use something like take batch if you want to see part of your data, because it materializes, in this case, 10 rows in the pandas format. So for example, here you will see that we have this nice data set about transaction memories. There are different batch formats, of course. Pandas, NumPy, whatever default, which is a dictionary, you can decide. Usually pandas is the one that's easy to understand. Again, columns. Here it's again, it prints the columns, the schema, etc. And then it can do, again, drop columns and take batch. We just, as you can see, it drops the column and then takes the batch. Drop columns, it's lazy, so it's just a plan. Here, you take the batch, you execute. So in the end, you see that we lost a column, basically. You can do the same thing with adding. Again, it's left as an example here. In this case, we are adding the dollars column. Add column is lazy, take batch, you materialize. And here you can see that this is just a pandas operation, as you can see, a mapping function. And we created this new column here. And in the end, what you can actually do is use this. If you have many operations that you want to do and do it in batches, right? You can use this map batches. So basically here, we want to let's think about what we want to do here. Let's say that we want to build some features, extra features. We want to do feature engineering, basically. Map batches, in this case, is kind of a big deal because it runs this function, parsing batches, on multiple workers for multiple batches in parallel without you needing to writing any distributed system or code. This is like normal pandas logic. And what this does, it's that Ray distributes everything and is doing, everything in parallel. It's really easy. The power of this is that you can do a lot of stuff for really, really large data sets. This is a count operation because you can do also sorry, I forgot this. You can do a drop in the same way. Here we dropped some column based on some logic. And then you see that the difference with the count is 6 and 96. So we basically drop this number of columns. Here, again, the principle is the same. It's just some example. You can do logic with this. You can even put arguments here. As you can see here, there's this category, right? You wrote this function, and the category, it's an argument. But with map batches, if you define if you decide that you want to use this function, you also can supply function argument and then materialize and take all, basically. In this case, we materialize everything. We convert it in a data frame, and we can see how the data frame head is. So this is basically, there's a lot of logic that you can do. Another interesting thing is the grouping part, which is a little bit, you need to think about it a little bit more in this case. So here is just a pure group by. Yes, sorry, here. And if you remember, there's first of all, you need to think about this. One of the most complex operations in terms of expensiveness, in terms of resources, is the shuffling of the data, because it amounts a lot of network trafficking. There's a lot of memory pressure because you're moving stuff all the way. And usually this is the usually a culprit. And in this case, we are doing a group by, very simply. We first do the group by, then we materialize with count, and we see at the end, it takes a while, but we see that we are actually doing this count by year by state. But again, of course, then we can plot everything. Again, it's just an example, but then if we want to apply some kind of complex logic, the group by a sort, so this moving stuff that is going around, here we introduce kind of a second grouping tool that can be a little bit more helpful, which is the map batches and map groups. So the map batches, which is the older one that we had, applies function per batch. So there's no grouping guarantee. But this one instead applies the function per group. Okay, and this requires kind of a grouping and shuffling. So this is one that takes a lot of resources. But with this specific function, it's actually very easy to do. It's not a burden anymore. Because here, what all of this does is that for each group defined by year and the category, it returns exactly one row, as you can see here, which is the earliest transaction. And to run this first transaction of year, Ray kind of needs to materialize the entire group, as Pandas does data frame on one group, on one worker, sorry. And this kind of implicitly says that each group must fit in the memory of a worker. And map groups, it's powerful, but sometimes risky when the dataset is kind of huge. So when do you want to use these map groups? Usually when you want to give a first, last, or most extreme item per group, or run a custom per group modeling or something like that, or you want to do a complex per group logic, which is not usually expressible with built-in aggregated, like, I don't know, group count or groups or something like this. So this is another thing that you should keep in mind. You can use this. And in the end, again, you have basically the most extreme part. And I think that there's some exercises that maybe you want to try during the break that I think should be right in 5 minutes, if I'm not wrong, for 30 minutes. And this is the part of Ray that I wanted to show to you. I didn't go like immediately to ray train and tune. I know most of you probably are interested also in this part because you want to train models and fine tune everything. But I thought that giving like a solid basis on how ray core works and ray data works will be helpful also for train and tune. And I also wanted to give you these notebooks, which is all this explanation with a lot of references that you will go through to actually establish a good, let's say, training loop using Ray. Just to give you extremely quick pitches for this, is that Ray has also this, part which is specific for training, which basically manages all the steps in machine learning. The data streaming, processing, training, tuning, serving, and learning, basically, and reinforcement learning, sorry. And this part is regarding the model training. It's something that you plug on top of, PyTorch, DeepSpeed, transformers, TensorFlow, Keras, Horovod, XGBoost, whatever you want. And I'll go in detail to the meat part. Again, I want you to read about this, is that you can define your model, whatever it is. In this case, it's a training function for that should go to each worker, basically. You also have the data loader. The only thing that you need to change here is to prepare the data for the data loader and supply some type of scaling config, number of workers, to use GPUs, and so on and so forth. And then you will see that you run this torch trainer from the Ray, let's say, library, and you will get, without setting any distributed data parallel, specifying the device where everything needs to go, everything is mapped. And at the end, you get the model in the location that you want. Again, I encourage you to look at this. You will understand much better now that you have the core concept at your hand. Same thing with Tune. It's another plugin that lets you do hyperparameter tuning using plenty of different frameworks like Asha. You can use Bayesian models to pick up the hyperparameter tuning and so on and so forth. So go instead to the RAG folder, in which you will probably see these three shell scripts. We will only need to run this one because this one is just an environmental config for you if you want to replicate this. I'll just show you. It's just load and install everything and download the models that you will need. And the second one, which one start VLLM, it's basically a script to set up the LLM that we are going to use. RAG, as you may imagine, is something more downstream application, which doesn't really need in itself parallel resources, but it needs an LLM, which needs resources. So what I set up here, it's with this, it's a VLLM server exposing an IP address that it's composed of 32 CPUs, but 4 GPUs. It's a model, it's a Mistral model, 24 billion parameters, so it's not, let's say, huge. And then we will connect to this IP, especially this one, in the worker node IP, but I'll give you the IP to connect to. Again, then if you want a little bit more details, what I've done here, it's a general VLLM serve, giving the model itself, the host and the port. Tensor parallel size, it's 2. In this case, it's just 2 GPUs, but it's enough. I just reserved a node for this. Then we have the guided, sorry, there's something that, we have the parallel size, which is the number of nodes, the pipeline parallel size. In this case, it's just 1 node. So this setup also works for more than 1 node. We set up an API key because we need to. It's very simple. We use the tokenizer mode for Mistral and general configuration. And we will enable guided decoding and explain later what is needed for. Technically, also for tools. I don't know if we will manage this, but I'll give you the notebook also to set up a small agent, RAG agent, and you can play with this. The thing that you should run is this start Jupyter, which is identical to the previous one. And we open a new notebook, basically. So let's do as batch to start Jupyter SH. And let's check that everything works. Yes. Then 2 things. There's the Jupyter output. As previously, we have this. Copy. In a new shell, open shell, not a Leonardo shell, your local one. Let's set up the double tunnel. And open this one. All right. Let's start with this. You should probably be able to get to this point. It's very simple. And so let's talk about RAG, which is a little bit different of what we discussed previously. RAG, it's Retrieval Augmented Generation. It's basically used to inject knowledge without doing fine-tuning of models, of LLMs. So this is the core idea is to search for the answer in a certain knowledge database, and then respond to the answer of a user. So a base LLM, let's say a large language model, has knowledge baked into weights from the pre-training phase, right? And updating this knowledge by training or fine-tuning is expensive, slow, and risky. Expensive because you need computational resources, a lot of them. Then it's slow because you go through steps of post-training, basically. And then it's also, it's not really applicable for many different cases, because again, this may be constraints. Maybe your organization doesn't have the computational resources to do so, or you don't really want to do this. Also, it's dangerous doing fine-tuning because you can basically get to catastrophic forgetting. If you don't do a fine-tuning in a correct way of these LLMs, you basically change the weights so much that you forget previous knowledge, and then you get an unusable model in the end. RAG, Retrieval Augmented Generation, instead treats your document as a kind of external updatable memory. So when a question comes in, you basically retrieve parts, snippets of the answer of the documents that has the answer, and inject these snippets directly into the prompt. So this is an example of how it works from an architecture standpoint. There's a user that makes a query to a certain app or a website, then triggers the retriever model that with find relevant docs that searches the database for certain documents relevant to the user query, then sends the query together with the relevant chunks to the LLMs that gives an answer, a contextualized answer, and then the app and website displays the answer to the user. And this is really, I mean, many companies and applications in general likes it because you can use it also with internal docs like procedures, manual policies, sensitive data. If you host it by yourself, an LLM, and you build up your RAG system, you may query your own private knowledge base. Updating knowledge means just re-indexing documents in your knowledge base, not retrain an LLM. So it's easy to pluck out documents that aren't relevant anymore and insert ones that are, relevant now. And this is basically, again, the main features that RAG has with respect to fine-tuning. And today we will go through an entire process of increasing complexity and also doing some of the steps that are needed to actually build a relevant RAG system. So in essence, is building a testing data set and understanding how to do some small hyperparameter tuning in something that you can actually tune inside a RAG framework. So first of all, imports. And then before running this environmental configure, we need to change the VLLM OpenAI endpoint. And I give you the thing that you have to paste here. Out. So it should be this thing. We will change it immediately. Okay, I'll put it in the chat. The OpenAI-like endpoint that VLLM exposes and we are going to use. So this cell, so I'll run it because it's very simple, and also this one. So first of all, what happens here? We pre-downloaded some embedder, re-ranker, and LLMs. We'll explain later why do we need all of this. We have some location. This change, if you this could stick with this. These are important. Also, please check that you put 0 here. I think the version that you have in the repo has 3, but put it 0 because there was an error. What are we doing here? Here we are establishing a connection to the OpenAI-like endpoint that VLLM exposes. So basically, all these models are exposed as servers, right? And then the chat OpenAI library became the standard on how to interrogate these endpoints, in which you basically send requests and get the responses. So here we have the base URL, the API key model, then we set the temperature of the model to 0 for reproducibility. Temperature is the way the model is created, let's say in a very basic way. So putting that to 0, it means it's reproducible, basically. So you can reproduce it in a deterministic way in a certain sense. And then we stick to 3,000 max tokens to be outputted. So why do we need a RAG system? Let's use our out-of-the-box Mistral model and ask question about Leonardo, so the supercomputer. What GPUs are available? Is there any partition without GPUs? What GPUs are in the cloud, etc. Then we can run this cell. You can do it and follow along. I pre-ran it. you will probably see that, first of all, as of my last update in October 2023, this means that the knowledge cutoff of this model is pretty old, and it doesn't have up-to-date information. Then here you will see that the answer to this question is extremely generic. It's not really good. It's not up to date. It doesn't have the information that we want. This is true for all the other information. For example, here it's talking about the generic cloud. We want to want the model to say something about the Chineka cloud. So it's this is a problem in a certain sense. And we can continue. Again, you should see probably this streaming of tokens. What happens here? Using our LLM with .stream and setting the correct framework, which is a list of this system and human messages, you get the correct answer and just the end answer. Chunk content is the streaming part, basically, that happens in real time. And we can basically do something different. Let's say we have the knowledge base, right? And let's try to put the entire document to the inside this in the context, let's say, of the LLM. So basically, we give a system prompt. You're an helpful assistant to answer, etc., etc. And then we explicitly ask him, given the following data, this Leonardo part, what are the names of the quality of service queues available on the Leonardo supercomputer? And then we append the data directly. What happens is that we get the actual the actual output. So this is what we have as queues right now. So now let's go a little bit more into the details, right? So we were going to implement a classic RAG, let's say. So we are going to apply certain techniques, different techniques. In this case, is again, as you saw, we are doing online, let's say, query with our VLLM server. And we are going to do stuff like a semantic search, nearest retrieval, and all of these interesting things. You have to remember that a RAG retrieval is, first of all, a search problem. It's an LLM problem second. We will not meddle with LLMs at all, apart from sending requests. And there are many different, let's say, parts that are needed to do retrieval augmented generation. First of all, you need to load the documents from a certain data source. Then you want to divide these documents in smaller chunks, smaller bits of text. Then what you want to do is store these chunks in a vector database, because we're going to convert them in vector DB, in embeddings, and then store them in a vector DB. And then you want to retrieve the relevant data using some techniques, again, like semantic search and so on and so forth. Then at the very end, only then you want to pass the retrieved data to an LLM for generation. The step 1 and 3 are basically offline. in the sense that 1, 2, 3, sorry, the 1, 2, and 3 are offline. So they are HPC friendly in a sense that you may have a large document a large document source, and then you want to parallelly do parallel embeddings and then put them all together in a certain database. You can do this offline, and then you just have the database. But then the retrieving and the passing, it needs to be online because it depends on a user query. Okay, and so the classic information retrieval approach. There's different ways you can do, of course, retrieval. One of the oldest ones were depending on bag of words or something like this, TF-IDF. Maybe you are familiar with some of the terms. But basically, you calculate, I don't know, the frequency of words in a document and in the query and try to match them. Direct keyword match, bag of words documents. These are the older ones, and while they are very fast, they, of course, as you can imagine, they may be very imprecise because they don't have semantic knowledge of what happens. And semantic search is the, let's say, most recent way of doing things. At a very higher level, semantic search uses embeddings because you represent documents, chunks, and queries as vectors. You try to then capture the meaning of the words and their full representation in very large dimension embeddings. So it's rich representation and allows you to understand that car and automobile, for example, they will have vectors in this embedding space that are close by. Then you can say, maybe if I calculate, for example, the cosine similarity between these two vectors, if it's small, right? If the similarity is high, so the distance is small, probably these two words in this case, car and automobile, are close in meaning. Same thing in this case. We have here the example: heart attacks and myocardial infarction, which are kind of synonyms or adjacent in meaning, and this is something that you can capture with this embedding, basically. You do this with the encoders, which are transformers, basically. So there's many different layers of bits of transformers, and then you have the words that go in. They become context-aware embeddings, and then you sum them and you create the embedding on the entire phrase. That's basically what you do to create these embeddings. Then let's talk about this other thing, which is important. We mentioned chunking. You will understand this if you think about the embedders. So the embeddings in general have a limited context length. So you cannot supply infinite long input sequences to whatever model, especially the embedders. They tend to have context windows, right? And if you want to embed a full document, of course, most of the time it's larger than this context window. So you really need to chunk it, divide it in bits that need to be smaller than the context length of the model that you use for the embedding, so that you don't miss any information. What happens is if the document is longer than the context window, is that it truncates it, so you miss part of the information. Another, let's say, byproduct of this is that dividing the document in chunks, you have smaller semantic bits that you embed. So it's actually much more efficient in terms of retrieval, doing embeddings of small parts rather than the entire document. Because as you can imagine, if I embed an entire document in a vector, let's say you dilute the information a lot in the embeddings themselves. If I have smaller chunks, right, smaller entities, let's say, I dilute less information, so they are a little bit more precise. That's what you want to. That's why you want to chunk. We are going to use some of these models. For example, see here some of 8,000 tokens at maximum, 384 tokens as a context length, 256. So the limitation depend on the module, and this is an upper bound. So remember, if you want to use an embedder, which probably should, you also need to understand what is the context length of the model. So let's first collect the input docs. We have basically scraped the entire Cineca HPC wiki, and we divided here in the input path, in the folder that it's in the input path variable that we set at the beginning, all this information in txt files. So we have all of them. Then we will introduce, now bear with me, I won't go too much into detail, but it's for convenience. We will use a library called LangChain, which is basically, I want to say the standard, because it's not true, but it's a library useful to fastly prototype this type of application, because it gives you data formats that are really easy to use. So what we are doing here is that we are creating a list of documents, and we append some metadata to it. A document is not other than a document constructor with some metadata, again, the doc name and when it's being scraped on, and the page content. It always has this page content, which is the content of the page, of course. So it's the all the tokens that are in there, all the characters that are in there. And then we would start to think about how I can chunk this. What's the most efficient way to split this document? And there are different ways of doing this. Usually there are three different families, let's say. One, it's fixed length splitting, which is the simplest. And you just say that you cut your document at a certain intervals. For example, you want 200 characters, you split after 200 characters, and so on and so forth. Of course, what it means is you can cut sentences midway, which is bad in terms of semantics, as you can imagine. Then you have this recursive character text splitter that are based on characters still, and they try to keep chunks under certain limit while respecting some separators and delimiters. For example, the punctuation /n, so new paragraphs and so on and so forth. This tends to be the first thing that you want to try because they are good default. Then you may have, but this is very document specific, format specific, again, text splitters, in the sense that maybe you have Markdown, HTML, Python code, or whatever. You know that you can divide, for example, with double hashes. You have the, a title in Markdown, and you can divide with them. So it's specific separators. So let's go into look at some of them. Let's try this character text splitter. Again, this is a LangChain class, basically, that you can use. I won't go into detail. Again, this is more an example, but you will have all the three of the notebooks, so you can play with this. This, I don't remember if I did everything. I'm really sorry, because I'll follow along. Let's hope that I remembered. Okay, perfect. So let's try the character text splitter again. And you can see here, the split is in the middle of a sentence. So it's not, that's not very good. Another thing that you need to look at is this chunk overlap. So what is chunk overlap? It's basically you maximize, let's say, uniqueness, minimize storage, of course, but you kind of have boundary problems, because this means that your chunk are strictly divided. But you may think that you want some overlap. So the end of a part of a chunk, it's also the beginning of another one, because maybe, again, you will try to limit this problem of hard cutting at the middle of a sentence. So it's something that you can also think about. All of these are hyperparameters of your RAG system, but here we're just showing them for the time being. Then we will have this second thing, recursive character text splitter. In this case, you will see, again, the stop, its maximum chunk size is, again, 100 characters. But these are a little bit more aligned, as you can see here, that it's kind of divided. This is, I think, a table or something like that. So it's divided in a little bit more logical way. But you need to remember another thing. All this that I showed you up to now, it's character splitter. But I was talking about tokens, context window in tokens. So typically, what you want to use is some way to chunk based on token, right? And let's use the embedder that for this specific lesson in this case, which is, if I remember correctly, I'll go up again because I forgot. It's, yes, the BGE M3, which is kind of a standard. It's a good all-around embedder, very simple. It should have around 8,000 as a maximum token. Exactly, max sequence length. It's this one, around 8,200. And so also note that the way that we set up the cluster, in this case, the center transformer will use the GPU because we have one available. Luckily, LangChain also offers us classes in which you can chunk per token. So we'll try to just use it right away. And you will see that using of course, the same tokenizer as our embedder, because we need to say the same thing. Here you will see that now at least we are sure that we are counting, let's say, in tokens at this time. So this is preferable. But we have a problem, is that the method above doesn't really support doesn't really support specific separators because it just doesn't work like that. And you need to work around a little bit using, in this case, LangChain, using a recursive character text splitter, but from Hugging-Face tokenizer. In this way, we explicitly state the tokenizer that we want, that we don't want any chunk overlap, that we want a chunk size, which is the max sequence length, and also we separate based on these separators. As you can imagine now, we have documents that are smaller in tokens that most of the time that are smaller in tokens that the maximum amount. So in this case, the document has not been split, basically. So it's full. So up to now, you will see that the problem of how to divide your documents is complex. You have to think about characters. You have to think about tokens, about separators. So there's a lot of design space even here. But the other important thing is that the chunk size is kind of a parameter. You want to optimize for that. So you need to find the right chunk size that will maximize the information content inside each one of it. In general, you have this kind of a trade-off. Big chunks means you have fewer vectors, kind of a cheaper indexing part, but the topic is diluted, as we were saying before. So you may have worse retrieval precision, let's say. Small chunks means that you have more vectors, you have a bigger index, bigger vector store, so this needs to be managed. But in general, you may have higher precision. You still risk, if the chunks are too small, to lose context. And to choose a chunk size, what you can imagine, you would need a evaluation data set. And if you don't have it, the fastest way to do it is to generate one. And what you need usually at the bare minimum, it's a question-answer pair, which means that you have the question and the chunk that answer to this question. If you don't have it, as I was saying, you just build a synthetic one. And this is just an example of a function that generates this synthetic dataset. I'm not going to run it because it will take, no, actually it's pretty fast. So if you want to run it, I can stop generating it, but I have all the outputs. So I also won't use our server, but you have it, you can try. This function, it's divided in two. You have a kind of a lightweight container that it's basically a data structure. We want to have the document name, the question, the answer, okay, the start and the end index of the chunk that answers the question, the chunk size in tokens, and the seed that we use to create the answer. And the generate QA pairs takes a certain document, the embedder, the LLM, and the seed, and generate this data structure here. And what is doing basically? It let's go through quickly. It sets the random seed. It builds the chunker basically from our embedder, and also the separators. Defines the separators. Then here I chunk it. Note that here I'm just randomizing the chunk size because I want a richer data test set. Basically here I'm saying it doesn't matter. Maybe I'll just define chunks of different size, whatever they are. Then what happens is that, of course, I add metadata to it, and then I create let's say a synthetic prompt, basically. So what happens is that two things are here important. First, I have this prompt. Now I'll recover it in a second, so I'll show you exactly what it is. It should be, okay. It's really simple. Given the following document, generate a single question related to the content of the following paragraph. And when generating the question, use the following format. Question, your question, which is a detailed question created based on the content of the document. Now you may think, but how can I make my LLM to stick to a specific configuration, right, of the output? Usually they start to generate. Well, there's this technique called, let's say, guided decoding. And here you can use it using this chat OpenAI with structured output and giving an answer format, in which you basically force the LLM to have a certain pattern in output. In this case, we are forcing the model here to answer in a JSON format with a question and the question in let's say in text. Because the point here is that we are supplying chunks of different shape and form for each document, and then we generate a fake question based on the chunks that we provide. And here we return the, let's say, all this data structure with everything. Since we have many documents and many possible different configuration of random sizes of chunks, here we can do, let's say, parallelization in a certain sense. Why we use thread pool executor here? Because basically it's just I/O. We are calling the server. So the parallelization here is very simple. It's mostly I/O bound, as we're saying, and you just set up the threads and basically keep the client busy while it generates everything. You can try it yourself. You will probably see something similar to this. Probably a little bit with a longer wall time, because each one of us is basically calling the same server. So it's kind of flooding it a little bit. And if it goes to the maximum capacity, your requests are going to be put in the queue. So it will probably take a little bit longer in your case, but whatever. If you want to run it, you will probably see different numbers. And what we get in the end of this is this type of data frame, which we have the original doc, okay, of course the seed, the number of chunk sizes, I'm sorry, the number of tokens of the chunk that we are generating, the actual chunk here, that's called answer in this case, and the synthetic question. Also, we have the start and end index in terms of characters of the string. This will be useful later, so we want to keep trace of it. And we save it. There's also, if you don't really want to regenerate it, it's much more easier to just load this one, this QA set. I pre-generated it, and you can find it at this this spot. You just load it, and we were going to use this. Now we have the data set, but what we miss is to basically define a way to evaluate the quality of our retrieval. And here we introduce the concept of mean reciprocal rank. And the definition is that given a set of question Q, you rank all available chunks, but their similarity to each question. And you examine the position of the relevant chunk within this rank. So, for example, in easier terms, for each question, we rank all chunks by similarity. Then you find where the right chunk appears to be in that ranking. If it appears in position 1, the reciprocal rank is 1. If it's at position 10 of the list of these ordered chunks, then the reciprocal rank is 1/10. You average across all the question, and you get the MRR. And why this is a good choice for evaluating chunking? Because chunking, it's you have to think of the upstream of everything, and a bad chunking schema makes the retrieval very noisy and bad, no matter what vector DB or LLM you use. And MRR captures basically how early the correct chunks shows up in the ones that you retrieve, which is exactly what you want to retrieve if you think about it. So the point of all of this is testing various chunks configs. And the idea is to find the optimal chunk size. This is a very long function that we'll go through in bits, just to give you an idea of what it does. I encourage you, as soon as you have time, to go through much more in detail. But basically, it first, again, splits the document into chunks with a specific chunk size that that is allowed between a range that we want to have. Then you embed all of them here, and you create the embedded data here with a specific structure. Just unpack all the metadata columns, because you want a nice, just for representation, you want a nice data frame. You compute cosine similarity between question and chunks. So what is going to happen here is that you embed also the original question. You embed all the chunks, you already have it, and then you calculate the cosine between the two vectors. The higher the similarity is, the more probable that the chunk has a semantic similar meaning with respect to the query. And so it means that it probably contains something regarding the answer. So we calculate all of this. For each question, we compute the rank of the chunk that contains the answer, which is basically all of this part. And then we compute the MRR, which is this part. All of this calculates the mean reciprocal rank. This is the rank itself, we compute the rank, and the MRR. Again, I'm not going into detail, otherwise I'll take all the time. But the point is, you need to do this. This is a kind of a blueprint of something that you can actually use to evaluate the quality of your chunking. And then we save everything. Then again, we run it. let's say starting from 100 chunk size to 150, 1 to 1500 maximum chunk size in steps of 100. It takes some time, test everything, right? And then we basically are going to evaluate the results. Here we have, for each chunk size, we have the MRR, and then the improvement with respect to the previous one. So how can we interpret also this plot here? Let's say usually when you have this type of plot, you want to look something like an elbow, because this means that you reach the smallest chunk size that achieve near maximum MRR. In general, you will also see that bigger chunks may improve the reciprocal rank, but in general, they reduce the granularity, can inflate the prompt size, because also your model needs to be optimized. Also, your model, the LLM, has a context window, and processing larger context window, it takes much more time. So this is something that you need to also take into consideration. And having larger chunks also increase the risk of hallucination, because larger chunks may have the answer inside, but also non-relevant context that are going to pollute your answer. Here, in our case, around 800 chunk size, around 100 tokens for chunk size is the optimum that we can get. So this, it's kind of a medium to large chunks, not extreme chunks. So it's something that is manageable. And again, this is a way in which you can programmatically, let's say, evaluate which chunk length is the best for your use case. In general, regarding model serving and serving all of this, you have to always keep in mind that chunk size, it's kind of a direct driver of prompt length, LLM latency, and cost. So even if we had the elbow here, probably we should still choose something a little bit smaller, because otherwise our application will have a high latency, high cost in token processes, and so on and so forth. Now we know the chunking. We have a value of the chunker that we want, but still we need to chunk everything and index all the documents. And now we introduce the concept of vector databases. In this case, we use especially one. It's called Chroma, through a client. It's one of the dozens of different vector stores that you can use. Here we just use it because it's also integrated in LangChain, so it's really easy to create all of this all together. You can use Milvus. I think there's some, exactly here. There's a link that you can check that compares different databases. Many also general purpose databases are introducing vector store capabilities, but in this case, we use ChromaDB. What is a vector DB? In general, it's a DB that does approximate nearest neighbor search very fast over high dimensional vectors. Because in vector database, we're going to store our embeddings. And so we want to search similarities extremely fast. You want persistence, so it needs to be persistent again. It should have metadata filtering. It's always good to have. A way to update it, and etc. Of course, now we are talking about an HPC setup, which maybe it's not the 100% best for this case, but in general, if you use HPC to persist like a vector store on a, for example, shared file system, you need to always be aware of the policy of concurrent writings, I/O bottlenecks, and all this stuff. HPC is really good to batch indexing and batch vectorizing, in the sense that you have millions of documents of dozens of pages each, and you want to create embeddings for all of them. You can do this in batches, and in batch populate your vector DB, right? So this is a good application for HPC. Otherwise, you can do it. It's a little bit tricky. Maybe this stuff it's a little bit more, intended for cloud usage, but you can do also with HPC. But let's go right in. We define our chunker with our chunk size, exactly. And we split all the documents that we have, all of them, all the documents. So here, for example, it's a document that is split in 2 different documents. And we also want to check, the chunk distribution, because it's always something that you want to do, but it tells you something about your corpus. In our case, we have usually most docs that are quite tiny, 1, 2, or 3 chunks, and not many that are long documents. And usually this, we'll talk about this later, this distribution of these chunks is going to affect metrics like a precision at K and recall at K. And also if a re-ranker helps, but more in detail a little bit later. Now we just create a vector store. And again, this is another function that you can kind of plug and use in your use cases in a certain sense. What it does is embeds everything, create a persist Chroma client using ChromaDB. In this case, it's a library. This is the method associated to the library. Optionally wipes the collection if it's not incremental. Otherwise, it creates a new collection or adds document to the same collection. Here it's the part that adds the documents and the metadata and every information that we may need together with the embeddings, of course. And here we just simply initialize it, giving the Chroma path. Again, we put it in our output path that we defined at the start. We create the dir, and we create our vector store. And again, here, in our case, there's no parallelization here. But one thing that you may nicely do that ties with what we saw previously, all these operations are independent. And you can set up array cluster that does this in parallel and writes our DB in batches, because all of these operations are completely parallel. There's no data waiting around or waiting for results of other parts. This is just a direct line for each chunk, basically. So it's something that can parallelize and make it much more fast. An example of how to use it, very simply here. Here we have we reload our embedder using the LangChain way of doing this. Again, it's it's just a subtle thing. Since we are working inside the LangChain framework, it has its own classes and so on and so forth for an Hugging Face embedder, for ChromaDB. And this is good because it also gives you directly a similarity search with score based on a question. So as an example, we have our embedder. We connect to the Chroma, and we supply the embedding function that we used to embed our chunks. And then we just do this. And what happens under the hood is that with the same embedder that we used for the collection, it embeds this and calculate the similarity search, the cosine similarity. And here you'll see that you have the information of, there's also the score here of similarity, right? So it gives you everything, the entire document, the metadata, and the score of different chunks that are similar. In this case, we didn't supply anything. We just give the default value, and it retrieves only 3 values. And maybe it's not really what we want. Maybe the information that we really needed could be in something a little bit lower in the rankings. We can always modify this between 3 and whatever we want. Let's try with 20. Of course, the output is huge. There's a lot of stuff, but they are ordered. You can pick up the ones that you want, as you can see here. Now we have another problem, because this K parameter, so how many chunks you retrieve, it's another, let's say, hyperparameter of our system. And we want to evaluate how many chunks we want to retrieve, because we don't want to retrieve too much information, and again, that floods the context window. There's the risk of hallucination and so on and so forth. We want to make an efficient system that only gets up to the point that I really need. So we want to optimize this K size in the retrieval step. And here we introduce precision and recall at K. So first of all, we again use the previously created Q&A set. Again, this highlights the importance of having a test set for this. And here we want to observe how the number of relevant chunks returned for each question change when we increment K. And a chunk is considered to be relevant in this case if it comes from the document that answers the question that we are evaluating. So the precision at K, basically it's the proportion of retrieved documents that are relevant out of the total number of documents retrieved. So it's the fraction or retrieved chunks that are relevant. The recall is basically indicates that for a given query, how many relevant documents were left out, which means that it's the fraction of all relevant chunks that you retrieve. All of this given a specific K. Then we can, again, now build kind of a large function. As you can see, it's pretty complex, but again, I will go through something that is happening inside here. For each question, so first of all, we have a K threshold, right? So basically a maximum number, a maximum K that we want to analyze. And then for each one of this, it's the range between 1 and the maximum K, we do a couple of things. For the time being, let's skip the ranking part. We retrieve the chunk, then we label the chunk if they are relevant or not, considering the chunk's metadata doc name is equal to doc provenance, right? So we are just calculating this. And then we calculate precision and recall using the same formula that we saw previously, which is very simple. The precision at K and recall at K is achieved over all the questions. So we need to do a mean of the results. So we can do precision, recall, and F1. And in the case of NoReRanker, again, this is the one that we are evaluating right now. We were just giving the K threshold here. So we evaluate different values. Again, we can just run this. We have the vector store, the Q&A set that we have, the max K that we want, and for the time being, NoReRank. So we evaluate everything, testing Ks for different configuration up to 20. And then we can plot everything in the line. Apart from the numbers, it's much easier to look at this graph. I mean, it's visually easier to look at this graph, but it's not really simple to interpret. So intuitively, what happens here is that at the increase of K, the precision drops. Many docs in our case are short of one chunk. So adding more results mostly adds noise. So it's not that important. And recall, why recall rises? But of course, for docs with multiple chunks, larger K covers most of them, right? So we are including more and more of these larger documents. This basically, we can also explain a little bit more what happens here. Basically, I already explained it. But the point is that with this figure here, we can also see if we can improve what we are seeing. So having even better curve moves in the sense that we should probably want precision dropping faster than this. Recall going higher than this, much sharply than this. And we can try to see if we can improve it with re-ranking models. So re-rankers, we briefly introduce them, and are specifically models that are trained for rank the document based on a query. So let's say that you retrieve 20 documents. The re-ranker ranks them regarding the query in even a better way, more specifically in terms of relevance and so on and so forth. So it's a second step that you can add to your retrieval mechanism. Specifically, we are going to use a cross-encoder, which is a way of doing this type of encoding, because usually when you want to do semantic search, use bi-encoders, which is the query and the documents are encoded independently into like fixed size embeddings. This means that there's no interaction between the query and the document. So often there's a sacrifice, let's say, in terms of the accuracy. In this case, a cross-encoder, a model that process a query and the document jointly, and then you get a relevance score in output for each document. So what happens is that you jointly encode the query with each chunk, and in this way, the model should capture more fine-grained interaction between tokens in the query and the document. This is the macro idea. So we do everything together right now, and then we rank them. And we go back to the function because it had the option. We have a re-ranker. We already downloaded it from Hugging Face, so we can, pick it. The only difference here is that if you want to use this type of cross-encoder re-ranker, you need this compressor. Basically, what it does is the top n, in this case, is the K threshold. So what we're going to do here is that we retrieve all the time 20 documents, and then we do re-ranking on all of this and see if the first two, first three, first four, etc., actually contain the information that we want. So it's a second passage. You first do a retrieve, a general retrieval step with a K, specific K, and then you do all of this second passage, re-ranking this 20 more closely with respect to the question. This is the most important part that you should probably get from all of this. We can reuse the function to do the same thing, and then see if we have any differences. So in this specific case, we don't have that much difference, because we can even plot the difference between these and the previous graph, which is very small, as you can see here. The large majority of documents, in this case, are short. Many of them and just one, let's say, one or two chunks or something at most. So re-ranking does not really appear to offer this benefit. Re-ranking is really important if you have extremely large documents that are comprised of many different chunks. So I'm going to retrieve, let's say, 20 of them, and then the re-ranker outputs the 3 most important between the 20 that you have retrieved, between using similarity search, let's say. Okay, up to this point, probably there's a couple of things that you have already seen. RAG is a complex thing. It's a retrieval problem rather than an LLM problem. You start naively with documents, and you try to supply all of them, and you fastly go into constraint regarding the embedding size, because all the time you need to pass through an embedding step in order to do similarity search between the documents. Since we are hard capped with the maximum of tokens that we may have inside an embedder, let's say, we need to chunk the documents. But chunking is not a trivial process. It's it depends, of course, the quality of the retrieval depends on the length of the chunk. So we want to evaluate what is the best strategy that we want to use. And I give you an example. Then, okay, we have everything. We need a vector store to put all our chunks that are vectorized. And then we can start to work on the retriever. But retrieving, it's not just I retrieve one chunk, let's say. I retrieve a certain number of chunks because the answer may be, let's say, may be connected to many different chunks. But at the same time, I want to optimize how many chunks I want to retrieve, because I don't want to retrieve so much more that I actually flood the information with unnecessary stuff, and my retrieval actually goes down in terms of quality. And we use mean reciprocal rank for the chunk size, and precision and recall basically for the optimum K, so number of documents you want to retrieve. So this is the lesson, the main lesson that you want to check. So with everything, we tested everything. We can write down a good, let's say, retriever for our use case, which has, let's suppose that we want to use, in our case, a ranker, because why not, since we have the opportunity. We have the embedder. We know that the top K, the best top K was 3 from here, it's around 3, this elbow here is around 3. We cannot use fractional numbers, so it's this point here, basically is 3. And we basically hard code everything that we want. The chunker, we don't need it anymore because it's already done. We just hard code the fact that we would use the re-ranker with the top K that we supply from the outside. And then we can test it again, very simply. Now the question, it's the same batch of question that we were using previously, and now we see that right here we generate the answer, we plot them, and it's much more on point in terms of the information that we wanted the model to actually output to the user. For example, GPUs, this is actually what we have. How can you associate a domain to a virtual machine? You can do that in Cineca, naming convention for a domain name for a virtual machine, Cineca AI, which is a module that we have inside of Leonardo, and everything. So the information here it's good right now. This is what we want, but it's not all, because this is kind of the bare minimum that we may have, especially if we realize that still one question is not very precise, because it tells you explicitly the QoS available on Leonardo supercomputer are not explicitly listed in the provided documents. So there's something that is not working, and we don't really know what it is. But this tells us that the system can be improved. This is another lesson. At the end, test it also to some question and try to get the feel of how it works. I know this is not really scientific, let's say, with respect to what I showed you previously, so the reciprocal rank, recall at K, and so on and so forth, but it's still good most of the time to, assess these also by feeling in a certain way. So let's, again, check this chunk. So usually when you have some of these problems is that the chunks are, there's some issue in them. So for example, let's take this text file, look at it, and what we'll see is that here there's a big table, and tables are always a big problem, especially if you want to chunk them and use them in a retrieval system. You probably know how they are rendered in Markdown. It's complex, it's difficult, it's a lot of text and spaces and so on and so forth. It's really complex. And let's say, in this case, it's that chunks are oddly separated, right? And in this case, adjacent chunk lack context of their position. So here, basically, what we are doing is that dividing We are dividing a large table in smaller chunks, but of course you lose information. You lose semantic information regarding the table itself. This is actually the table. As you can see, it's a pretty long table. In theory, we can tune the question, which is nothing that you want to do, of course, because you don't tune the question. You want to tune the system. But if we do this with just this minimal detail, we get a much better answer. What are the partitions available in Leonardo Boost and their associated QoS? Probably this question is much more specific, so it's much more easier for the model to, for the retrieval, I'm sorry, to find the chunks that actually have this information. But I mean, it's still the even if you look at this, you will see that the most relevant context and chunk is still missing. They are not extracted because this is actually something a little bit more. It doesn't have everything. The entire table is not there, so there's something that is missing. What we can do, first of all, it's realize that sometimes semantic search it's really good, but the good old method of doing bag of words or this kind of stuff can still be useful, and we can try to implement both of them all together and basically see that we can retrieve information when there's a strong match in the same words that are in the chunk and in the question. And only if this fails, so it's below a certain threshold, then go to the actual semantic search. And one of the most used bag of word method to do this is the BM25. Basically, there's a large assumption here, which is the more frequently a term appears in a document, the more relevant the document is to the query, which is a strong assumption, but it's the one that we, that's basically what we are going to have anyways. And basically, it's this is the formula. And it's calculating the occurrence of certain terms inside the document with respect to the query. Query is the query, this is the document. I'm not going to go too much into detail, just know that this is a way to check if some exact tokens are present both in the query and the document in a smarter way. And luckily, there's a library for this. It's already implemented. So let's try this. We tokenize everything. And we just tokenize here. So we take the page chunk as they are, not from the embeddings, so not from the vectors, just from the chunks themselves. And we calculate the BM25 scores, both for the query, in this case, which is the same as before, and for all the documents again. Now we calculate all these scores. These scores, they are ordered. The higher the scores, the better it is. We can see that still it's not what we are, what we really want. So this, let's say, this avenue that we wanted to basically to follow, it's not really something that we are going to pursue, because if you look at this BM25 that gives a higher score, it's just a general purpose chunk that's it's talking about architecture, cluster, some partition, etc., which doesn't really respond to what we want, same as the other ones. Then there's another thing that we can try, which is contextual retrieving. Even before going to this, I think you kind of got the gist of what is happening here. At a certain point, you try many different avenues and see what it sticks, right? So there's the option of doing a hybrid retriever with BM25 and older backup models, doing contextual retriever, do a hypothetical question, all these other things that are, let's say, advanced modes of doing RAG can be applied on top and needs to be tested. All of them need to be tested in order to assess if the quality is good or not. Here we use this contextual retrieval straight from Anthropic, from a blog post that they introduced, which is really interesting. The core idea of this is that for each chunk, you use an LLM to ask, given the full document as a chunk, what's the chunk's role in topic or section context? So basically, you give the chunk the full document, and it returns, let's say, an assessment of the relevance of the document inside the entire structure of the document. So for example, here, this is straight up from Anthropic. The task is please give a short and succinct context to situate this chunk within the overall document for purpose of improving search retrieval of the chunk. Answer only with succinct context and nothing else. So you invoke, you create everything, and you will see, again, it's the same thing that you saw previously. We're just applying this function. And see that for each chunk, we have also this this chunk is part of the hardware details section under system architecture, the random supercomputer, and so on and so forth. So it gives us a little bit of context. And what you do at the end, you can scroll all of this, is to embed everything again, so that now the chunk is the context and the chunk itself. You embed everything, and you try to do this again, the cosine similarity. And you will see that now it seems a little bit more on point, because this is the first part of the table. This is the second part of the table. This is the third part of the table, and so on and so forth. And these are the higher scores, of course. And basically, you have everything. Again, then what you want to do, this was a small test. You want to do this to all your collection. You delete it, you re-embed it all together. And now you have, you redo the testing, of course, because now you have a new collection. So you want to retest the k-threshold. Remember, always redo the tests. You get, again, all of this. You see here, now this is much higher, this intersection, basically. So it drops much more sharply. And even for smaller chunks, now the, let's say, the value here of the precision and recall and F1, it's much higher. So there's an improvement here. Even more so if you look at the differences. If you remember, we were at this order of magnitude previously, 0.01 or something. Now the improvement is significant. It's starting to become significant, especially even for smaller case. And all of this you can you redo the semantic retrieval that we had previously with this new top K that we defined, the new collection name that we stored in Chroma for the new embedding chunks plus context. And now you get, if you do this, let's say if you ask this question, you actually get what you want. We are basically at the end of the end of both the lesson and this first notebook regarding RAG, which gives you kind of end-to-end vision of what doing RAG really is. It's not just, I'll take some documents, I just blindly chunk them, put them in a vector store, and then do semantic search. You need to look into many different hyperparameters. Okay, I have many documents. How do I want the chunks to be? What they are? How can I divide them the best way possible? And I have a way to measure this. Then you embed all of them. Which embedder do I want to use? Larger dimensions, smaller dimensions, so efficiency rather than, I don't know, precision. And then when you have your collection in your vector store, you have to think of, okay, how many documents I want to retrieve for each question? How can I maximize the correctness of the first ones that come up in this list of documents of chunks that come? How can I maximize the relevance of them? And you have ways to directly measure it. This notebook, you can use it as it is, adapt it to your application, and it gives you basically many things that you need. And then you have a full retriever. But then you can think, okay, let's be smart and think of ways to increase the information content of each chunk. For example, do this a contextual retrieval, or maybe do other techniques, or maybe try to stick also an older method. Maybe there's a question that have a direct match to some specific keyword that I want to retrieve immediately, very quickly with a BM25. So it's something that you want to apply on top. And all of this contributes to the quality of the system, right? So the other very important thing that always misses, this is from experience, always misses when you want to build this RAG system, it's a good set of expert-made questions to quantify the performances. You either have the experts that are going to, by hand, write down a question and identify the chunk that answered this question, or you can use this synthetic data generation that I showed you previously, trying to use a larger LLM to generate the all the this data set. This is another thing that can be done in HPC, because you can think of this problem as a batch inference problem. You use a Slurm job, you spin up a model, then you batch request to this server that you have spun up, and then you get all the you get your data set back. And at the end, you release the resources, and you don't waste, let's say, compute time or let's say node hours that you have in your budget. Let's say. So it's pretty complex as an argument, let's say. And another thing that I don't have time to go into, but I want to give you still, that could be interesting for you, is to move a little bit beyond the pure retrieval part, and let's talk a little bit more about the deploy. So if I have everything, how can I evaluate? I can set up a workflow-based approach, and also an agent that does the RAG, which is another buzzword that you probably have heard about, agents and so on and so forth. Here, there's an explanation of using LangChain and LangGraph to create a graph, a React graph, so reasoning and acting graph, in order to ask questions, even generic question, and make the LLM query your vector database only if it recognizes questions that actually need context to be resolved. So, for example, we can have a setup in which I ask my LLM what is the capital of Italy. You don't really need to do semantic search on our let's say our vector database to respond to this. It's probably baked in the parameters. But if I ask questions about Leonardo, probably on the random computer, of course, probably I need to go to search my vector store. And an agent system actually does that. And here there's, again, a blueprint on how to set up everything from scratch. Also, another interesting part that I suggest you to really read, it's this part here with the guided decoding. I just went through really quick about guided decoding, but it's a powerful tool to make an LLM, let's say, spit out only the exact data format that you want, basically padding all other tokens that you really don't want to. So, for example, here with guided decoding, if you need to fill a specific data format, like in this case, let's say, you can force it to spit JSON with just name, age, and so on and so forth. The example that we have here is just a selector for different collection inside of our database that we force them to be just 4. And with this setup, you can force your LLM to just structure the output in a specific format, which is very powerful if you want something which is like, for example, a router between selecting different collection here, for example, to do RAG, or routing between other, other parts of your system, and so on and so forth. So I think with this, I just have 4 minutes for questions and so on and so forth. You have at your disposal everything. I think that the VLLM server that I have should be up for other 3.5 hours. So if you want to play with the model that I have, hosted on Leonardo now. And yes, this is basically it. Of course, if you have any question, feel free to. We have like 5 minutes, or otherwise write them in Discord, and I'll try to answer as best as I can. And hopefully, this was interesting. I know it's a little bit less hands-on, but the topic is really vast. There's, I think, a lot of interest in how to set up these systems as best as they can. And since we had this experience, I think it was interesting to share. So hopefully it was interesting to you.
This was already announced. So I'm going to talk about hyperparameter optimization. I guess so there is some overlap between, well, maybe first a few words about me. So my name is Oskar Taubert. I work at CSC, so the Finnish National Computing Center, as a machine learning specialist. I guess in the past year or so, I haven't really done much with hyperparameter optimization, but before, like parts of my PhD was on that, and I'll actually present some of my work later. So, but not exclusively. So this is not just an advertisement. Right. So maybe about those terms, I guess AutoML would encompass both of these things, hyperparameter optimization and neural architecture search. I would say, well, I usually talk about hyperparameter optimization, and sort of mean that also kind of all-encompassing. Neural architecture search is sort of usually more specific about the architectural hyperparameters of a model, or specifically a neural network. That's why then often hyperparameter optimization, the term is then used to only refer to the other parameters. That sometimes makes a difference because sometimes you choose different algorithms. So, well, very often when, or I'm assuming that when you teach about machine learning or neural networks, eventually you'll be confronted with the question of, okay, you've taught me now like about neural networks, and there's all these parameters like how many neurons, how many layers, what like optimization algorithm, how do I pick them? And I guess usually the short answer is trial and error. And hyperparameter optimization or neural architecture search would be the attempt to have a sort of more formalized or more rigorous method to go about that. But yeah, it's not just about the architectural hyperparameters, it's also about the training parameters, and you might also think about like data parameters, like how to sort of pre-process, or like there's certain decisions you have to make about data batch size, for example, would be one thing. Yeah, you kind of, if you design models or neural networks, you at some point will need to make these decisions. And yeah, how do you do that? That's kind of the question. So yeah, I will talk about some algorithms. Like none of this will be exhaustive, so there's sort of always room for more. I will talk about some tools and implementations that would be kind of practical, or that might be useful to have some experience with. I'll talk a little bit about like scaling, how to do things as efficiently as possible. And then at the end, I will mention a few things that I definitely won't have time to look at. So yeah, if you are interested, then yeah, maybe these are next steps for you. So one important thing to mention is that so you have training data that you use to train the model parameters. Then you have some kind of held out data set that you are validating your model with once it is trained to like not overfit, and then or like enable some other things like early stopping, for example. And then, but you then need this validation data to basically optimize your hyperparameters. So that means you should hold back a third data set that is never seen during either of these processes. So in a sense, that should prevent you from overfitting on hyperparameters. And I think that is quite important to mention. Many sort of data sets that you just download have just two partitions. So you have to come up with a third one. So usually you have a training set and a test set, and you then have to subdivide your training set into two in order to get a validation set. But yeah, this should not be neglected. I think that's quite important. Maybe, so I already mentioned there's a huge number of parameters or choices that you have to make for like maybe a more complex neural network. It might be like tens, it could be even more than that. But they are different kinds. So and that's also what I mentioned about using different algorithms here. So if you look at something like learning rate or maybe dropout rate, like those are more, or especially learning rate, those are more hyperparameters of the training process, and they are more often continuous. That's sort of enables to use different algorithms. On the other side, set of the spectrum, for example, the choice of optimizer, whether you're using ADAM or stochastic gradient descent, or the choice of activation function in your model. Those would be categorical. So something like you cannot optimize those kinds of parameters with a gradient descent algorithm itself, for example. And then in between, you have integer parameters, something like the batch size, the number of layers, the number of neurons per layer, those kinds of things. Those would also be difficult to optimize with a gradient descent algorithm. And then kind of in the middle there, you have ordinal parameters. These are, I think, usually modeled just as categorical parameters, but yeah, some algorithms might be able to exploit that they are ordinal, so that they kind of have an order in which they go, but not a difference or a distance between the two, between any two entries. Yeah, and yeah, I already mentioned gradient descent as one possible algorithm that you, in theory, could use as an optimization algorithm for this as well. But well, in order to do that, it needs a gradient. So most of the algorithms that we'll talk about are gradient free. They don't need any gradients at all. And that is kind of what makes them useful in this context. There's of course, like, optimization is a huge field, and yeah, gradient free optimization is then kind of the subfield that is sort of more interesting here. So I already mentioned that trial and error would be maybe a good, or maybe not a good, but that's still done or practiced a lot. So yeah, there are more kind of there are two more algorithms that are sort of used a lot that don't require a whole lot of sophistication. The first one is just grid search. So you have your search space. You just each dimension that you have, you subdivide that into X steps, however much your budget allows, and then you evaluate your model, so which probably includes training your model and then calculating some validation score along these grid points. This has some potential issues. So the first thing maybe is that assuming that the performance of your model is actually not dependent on a certain hyperparameter, then you've just basically wasted a whole lot of compute. And that is something that random search already improves a little bit. So if you just sort of jitter all of these grid points a little bit, that already gives you more information. And if you just completely purely randomly sample, then yeah, you get more information in that scenario. And also, in a sense, you could think, well, I've done my grid search. Now I find, okay, I want more. I actually have more budget to compute on. For grid search, you then have to decide, okay, how do I kind of refine my grid? For random search, you can just keep going, just generate more random candidate solutions and evaluate those. So it's kind of less effort to extend the search, if you will. Yeah. That also already, it brings us to our first exercise. So I prepared 3 exercises. The first one is just like we'll use one of these naive approaches. I think now I just shared my window. But yeah, so the idea here is in the repository, there is, in the naive folder, there is a script that performs a grid search as an Slurm array job. So there's already a training script there as well that you don't need to modify at all. And the grid search, it just, it generates those candidates on a grid and submits those jobs. And each job is kind of run individually. It performs a training and calculates a validation score. And your job is now to take that grid search and just change it to do a random search instead. Yeah, I guess we could maybe 15 minutes for that. And if anyone has questions in the meantime, I can also maybe. Yes, thank you. So let's go here and let's. Yeah, so you can see there's also the train script. So I guess this might be familiar to you or something similar from an earlier exercise or a few days ago. So this is just a very simple network with 3 layers. We don't even optimize the number of layers here. We're just looking for optimizing the learning rate, the activation function, and the hidden dimension and the batch size. The training loop is already done, and you'll notice here at the end, we'll just pass these arguments, like as command line arguments, we'll pass the parameters that the model is supposed to be built with. And if we pass it a random seed, then I set it up such that it just ignores any defaults or any other hyperparameter. So if you just call this script with a random seed, it will do a random, like it will generate the parameters randomly. If there are no further questions, then I would suggest that you do the exercise until half past. Good luck and see you then. Let's go. Of our sort of array, the array job ID, or of that sort of the item in the array that we're currently at, as a seed. You could do something a little bit more sophisticated and modify it somehow, like maybe you don't just go from 0 to 7, but add some offset or something along those lines. But this sort of would meet the task. Of course. So this this kind of schedules, since there's no dependency here, you can just schedule all of them and they can run either parallel or not. It doesn't really matter, which is also a nice, that's actually a nice thing about these algorithms, that, yeah, they are kind of as much like as parallel as you want them to be or not. Of course, that as the downside that you are not really exploiting any of the information that you learn as you are optimizing. So if you are in the unfortunate method that you don't have like infinitely many GPUs, then you can only run a finite number of these evaluations at a time. And usually you will not run all of the ones that you want to do at a time. So yeah, there will be some kind of number of evaluations that you finish, and then you start the next batch. And ideally, you would want, you've already learned something about the search space that you are investigating. So it would be nice to exploit that information. And yeah, we'll talk. That's kind of the underlying idea of all the following algorithms that we're going to talk about. So there's a few kind of groups. So there's evolutionary strategies where you have the idea of like they're sort of inspired by biology in some sense, that you have some kind of survival of the fittest, and the fittest are then also allowed to kind of procreate. So their parameters will survive into the next generation and will sort of propagate into the future evaluations. Whereas the candidates that have not performed very well, they will be not allowed to do that, and so they will not propagate into the next into the population that you're optimizing on. And there's a few different ideas that you can sort of put on top of that. And yeah, I'll show both of them. There's of course way more variants of this. Then another major branch is Bayesian optimization. So again, there's lots of ways of doing that. The main idea here is that you have some kind, after you've sampled a little bit, you have some idea A where there are so far better performing candidates than like worse ones. So you have some that are better than others. And you also know where you have not searched yet. And you can sort of have some kind of trade-off between exploitation and exploration. So exploration going into the direction of where you haven't explored yet, and exploitation going into the direction where you know that there are good candidates there. Yeah, again, there's many ways of doing that. And then there are some sort of other things like particle swarm optimizations. They don't really, they're difficult to make work in a setting where you have categorical parameters. But yeah, they are still sometimes used in this context as well. And then there's Nelder-Mead, that the same applies to that. That's a kind of simplex optimizer that has even more constraints, but yeah, there are implementations of that around, and sometimes you are in the position to leverage them. Yeah. So then also, like on the technical side, there's lots of different of these tools that implement some or like a larger or smaller subset of these algorithms. So the first one I'm going to talk about is Optuna. Optuna is, I believe, the most like popular and the most widely used tool, and it implements like basically all of these parameters that we've that I've brought up, I believe. So definitely it has these naive approaches. It has different Bayesian optimizers. It also has different evolutionary optimizers. Yeah. Then Ray is like you've seen Ray in the previous session already. So you can use it on top of, for example, Optuna in order to kind of start many evaluations. But as it was also already mentioned, Ray and also Optuna are kind of tools that are more aimed at cloud environments. So that's the next. I think that's true for a lot of these these hyperparameter search tools. One that very sort of explicitly, where the point is that it's focused at HPC environments. That's Populate. That's work that I still am. Host of other tools that I'm not going to talk about this time, at least. There's Deep Hyper I find quite interesting because that's also I think it has more HPC salience than, for example, Optuna. And yeah, the SMAC 3 Navigrad, I think those are also kind of established tools that might be worth a look. In the end, I would say, so I know I mentioned there's lots of tools that implement lots of different algorithms that you might all want to use. So in a sense, we only postponed our decision problem where we don't know what to do. And now we have to pick an algorithm that tells us what to do, but now we have to pick the algorithm. So yeah, I think in some sense, or in some regards, some of these are then just resolvable by taste. Well, what is the tool that you're familiar with, that you're comfortable with? So you don't have to kind of overthink it. And maybe sometimes there might be some constraints of your search space that makes the algorithm that you want to use obvious, and then you just use your favorite tool that implements that algorithm. But yeah, in the end, there's yeah, you can't have it all, unfortunately. Yeah. So let's talk a little bit more about Bayesian optimization with the example of tree structured Parsen estimators. So what you do here is also, you start off with a random sampling of points that you evaluate, and then you can split them into a good and a bad set. And so you can already see from the picture, the good set is in blue and the bad set is in green. And the good set will usually be a lot smaller than the bad one. And then you can sort of try and approximate their distribution by just kind of overlaying Gaussians on top of them. And then it sort of gets you the distribution of those or it approximates the distribution of those sets. And from that, you can derive what's called the acquisition function. That's also a common feature of different Bayesian optimization approaches. And in this case, you just divide those two distributions by each other. That gives you what's called the acquisition function. And this acquisition function is supposed to, like the optimum of the acquisition function, that is supposed to be the next point that you sample. And yeah, so in this way, this is also why this is a very popular Bayesian optimizer, because it's sort of very straightforward. It's very, it's not too complicated to understand. It's because Bayesian sometimes maybe has a connotation of, oh, this is weird statistics. This looks at maybe like you could implement it yourself without much trouble. And yeah, actually in that blog post, I think that's a quite nice sort of introduction of that, and you could just code along if you wanted to. Yeah, so how do we then, so we have the acquisition function. How do we now get our next candidate? Well, we just use any other optimization function to find the optimum of that acquisition function. So if this is continuous, then you can just use gradient descent, for example. But you can also use this TPE on non-continuous or on categorical parameters as well. Yeah, and that gives you the next point to sample. Now, you might, well, if you are still in the situation that you might have enough resources to run several of these in parallel. And how do you do that? Well, one way could be that, so I said, for example, that we split this into a good set of candidates and a bad set of candidates. How you do that splitting could be something that you kind of vary in between the different workers that evaluate stuff in parallel, or that have to generate new candidates in parallel. And then this way you could run different evaluations in parallel that have the same information, but still make different choices. So you don't do unnecessary or like the same work on multiple workers and just waste all of that compute. Yeah, I guess, yeah, this is the basic idea of that. And this is also the standard algorithm that Optuna uses. Optuna is, I mentioned, it is kind of cloud focused. So you have these lots of different workers. So you basically lots of different Python scripts that say like that communicate with each other via a storage. So usually that will be a SQL database. At least, so there's multiple ways they implement this. You could have in-memory storage, but that of course only works if you have a memory shared. If you have a shared memory workers. If you are using multiple nodes on an HPC cluster, then that's not a given. So you would need some other approach. And then what they do is they have a SQL database on the file system that they use to communicate with each other. And that, yeah, that's not nice. That causes some issues. So in the Optuna example folder that we'll use for the next exercise, you can see I started working on a multi-node example. I also shared the link to the original repository where they implemented this. So on Leonardo, this didn't work because the SQL implementation I was using needed a newer glibc version than what is on Leonardo. You can very easily circumvent that by putting that in a container and running it there. But yeah, I didn't do this for this exercise. But if you really wanted to use Optuna on many nodes, then I think this would be, I think, the best way of doing that. Yeah, and it would be kind of, it should be fairly portable to different clusters, even though they are all different. But yeah, so we have all of these different scripts. They can communicate with each other through this storage. And each of them can then suggest a new candidate solution that they want to try out. They can then evaluate that, so train that. And once they've done that, they can report their result back to that storage, whether it's just written into the database and is henceforth available to all the other workers. So they can also use that information to create new candidate solutions. Yeah. Are there any questions on Optuna so far? Because if not, then we could just go to the next exercise. Yeah. All right. So yeah, the training script is essentially the same, except now we'll use Optuna on top of it to generate the our hyperparameters a little bit more, well, let's hope intelligently than we've done previously. So what you will need to do is first wrap your kind of training, like where it generates the neural network, trains and evaluates it, into this objective thing that takes a trial object. A trial is in Optuna thing that sort of contains everything you need to generate new candidates, and you can generate these new parameters by just asking for them. So in this here it would be trial suggest, and then there are different versions. So you can int, float, or categorical. There are some more versions of that. For example, if you wanted to do a different sampling, let's say you have a learning rate and you want to do a logarithmic sampling, then there's a function for that. But yeah, let's not worry about that right now. And they just, all of these take a name for that parameter. And a minimum and a maximum value, except the categorical. The min and max doesn't make sense. It just takes I believe it is a list. It might be also other iterables are allowed, that contains all of the different choices that you could make. And yeah, then I think all of the rest of that is already implemented. And then you have to create a study, which is the thing on a trial. So a study is essentially one hyperparameter search. So it also takes a name, and it takes one of these storage things. In this example, we will use this journal file backend. As I mentioned, there's also a shared memory backend, and there's a there's different SQL-based backends, but yeah, in this instance, we'll just use the journal file, and you just have to give it a path. And this load if exists true just makes it so that yeah, it loads the study if it already exists, because yeah, only one of the workers can actually create the file on the file system, so they don't argue about that. And then you just call study.optimize, and you tell it which objective to optimize, and how many attempts it should take. Yeah, that's it for that exercise. We could just do 15 minutes again, and then it's a bit slow right now. Do this folder. You can see, so in this multi-node folder, there is the multi-node example that I mentioned. And in this check results script, it collects from that journal file that you are writing, it collects these the results basically. And yeah, then in the this time you don't have to change anything about the run file at all, except you might want to add the reservation, because so I took that out at some point, but you can take you can add today's reservation, of course, if you want to. And then in the actual script, you would only need to look at the things that are highlighted with to do. So oops, here you take the trial and get the parameters from it, and down here you have to create a study and then call optimize on it. That's it. Yes. Good luck. Yeah, if you have issues with the exercises, or you think they are too easy, then yeah, maybe make that known with some emoji or some way that you find acceptable. Yeah, because it's always difficult to know the audience that you're going for. Yeah, so maybe let's look at we have time. Yeah, well, there are not many surprises here. It's pretty much just what I already showed. But yeah. This is what I had. I used, or I sort of treated the batch size as categorical, because yeah, no particular reason. It might make sense that for computational reasons that these are like factors of 2, or but yeah. Yeah, that's so. I guess, yeah, that was a basic Optuna example. Optuna has a bunch more features. An important one is pruning. So very often you can tell quite early into a training that maybe this isn't a very promising candidate, and Optuna can then prune these. And so essentially you have to call at the end of your like of an iteration or of an epoch, or like whatever is the appropriate interval. You can show you can call a check where you can then let Optuna decide to prune this this particular candidate. It's very similar to early stopping, but it can use some more information from all of the other runs that it has seen. So like for early stopping, you would just see, okay, my loss isn't improving anymore, so I can stop this training. Optuna can also tell, this loss is not as good, or it's way worse than all of the other candidates at this time, or it's like it will never reach the other candidates that I know of. So it doesn't make sense to pursue this training any further. Related to that, there's also something called successive halving. So that means that you start off with a population of n workers that are starting to evaluate. And then after some period of time, you will cull half of them, or like the worst half of them. And you can repeat this until only one remains. And that is then kind of the best candidate. And so that also just saves a lot of compute, and you can repeat this. And well, hyperband then is kind of a loop around successive halving, where that is kind of a grid search that kind of optimizes this process as well. And yeah, so this is also often a very good idea to only use like a smaller part of your data and a smaller part of your compute on every candidate, and only the promising candidates receive more of those resources. Then it has some visualization tools. So in particular, a dashboard. I think the dashboard is quite similar to something like MLflow. So often I would usually use MLflow instead, because that's kind of more generic and you can use it with other things as well. But it might be useful. And of course, it implements a whole host of other algorithms, as I've already mentioned. So the next one I would like to discuss is CMAES. So that's Covariance Matrix Adaptation Evolutionary Strategy. And the way that works, it is you start off with some population, and the next generation of your in your process, you can determine by checking the covariance matrix of that population, and that kind of then deforms the distribution that you can sample your next generation from. And well, in the simple example that I've shown, you can see that over several generations, this distribution sort of widens and spreads until it encompasses the minimum that you're looking for, and then it kind of sort of converges down on that. In a more complicated optimization landscape, it doesn't look quite as tidy, but still you can see then that it kind of navigates through, if you have some kind of canyon that you in your optimization landscape that you go through, you can see that kind of like an amoeba kind of wanders through there. Yeah, so maybe this is a fairly this is an algorithm that I find quite interesting and I like. Unfortunately, I think this only works, or I'm only aware of implementations that need a continuous parameter space, so they don't work that well with categorical parameters, but still. However, so if you go sort of back to basics, just to a genetic optimizer, where you think of one candidate as a sequence of genes, and each gene can have, like, it could be categorical, or it could also be like a real valued number on integer or whatever. But every of your candidate solutions is just a sequence of those, we could call it genes, not the trousers. And you can then do a very the sort of original evolutionary optimization on that. So you have some kind of selection process. So from your population, from your first generation of candidates that you evaluated, you can pick the best ones of them, and they are allowed to continue. Well, they don't continue to the next generation, but they are allowed to breed in order to generate the next generation. Then from you can have 2 or more parents, and you can do then what's called crossover. So you can take some genes of either parent and mix them together into a new combination that you haven't evaluated that. And then finally, in order to get some more, a little bit more exploration into that, you can have just random mutations to modify your some individuals. And if by combining these different steps with each other, you can just generate a new population from an existing one. So you start off with a randomly initialized population, you evaluate them, and then from the best ones, you pick like those combinations of genes that are allowed to propagate into future generations, and you slightly modify them so that it doesn't get too stale too quickly. And yeah, this is kind of a more a basic evolutionary optimizer. The nice thing about this one is that it's really kind of versatile. So that one definitely works with categorical parameters, and it's kind of very straightforward to implement. Yeah, that's why this is the kind of the default optimizer that Populate uses. And yeah, so Populate is the next tool I want to talk about. I've already mentioned that this is focused more on HPC. So, for example, it doesn't use the file system or like a SQL database in order to communicate between the different workers that do like parallel evaluations. And it also doesn't have a centralized authority on generating the next candidate. So every worker generates the next candidate in order to then evaluate it. And this is what I called lazily synchronized. So we kind of we do only asynchronous communication between workers. So in the context of this evolutionary optimization, you can think of it as you have a bunch of you have your population. The individuals in that population are evaluated. That can take a variable amount of time. If you think of your neural network, for example, and it has you're optimizing the number of layers that it has, or some hyperparameter that has an impact of the number of parameters or the number of floating point operations that you need in order to train the model. Then, of course, a more complex network with more parameters will take more time to evaluate. And so therefore, you might lose actually quite a bit of performance if you were to have a synchronization barrier after each generation. So that's where this kind of asynchronicity comes in. So each worker will, once they've evaluated one candidate, they will just generate the next candidate and start evaluating that without waiting for every other worker to finish with their with the candidate they are currently working on. They will just receive the information that they have gotten in the meantime, because yeah, you can exchange information asynchronously. Yeah, so in this sense, you don't have this kind of notion of a generation as you had previously in the like as you normally do for these population-based algorithms, or at least the evolutionary ones, but you have kind of the softened notion of a generation. And I guess you can sort of apply this to all manner of different kinds of population-based algorithms. Whenever you have this kind of notion of a generation, you can kind of soften that a little bit for computational efficiency. So how does that maybe work in a little bit more detail? So here we have like two example workers, and we have already a population here with three individuals in it, and in order for them to perform the next step, the worker can just apply what we call a propagator. So this is essentially just the sampling algorithm. So we could use a genetic optimizer, or it could use something else. For now we'll just, you can stick to thinking of the genetic optimizer. It will generate a new candidate, and it will then evaluate that. And once it has evaluated that, it will integrate that individual into its own population to be used for future generations, or for future, to create offspring if it was good enough. And it will also asynchronously send it to all of the other workers, so they can also use it for future. So you can see it will be sent here, and it will then arrive at some point in the future. So we are using MPI for that, and MPI can do all of that asynchronously. So this information, it is stored somewhere in the network in between those two workers, so they don't have to like handshake on it. They don't have to like send like acknowledgements or any of those things. It just gets sent off, and at some point in the future it will arrive. Right. And then the same thing, or the same process just repeats again until, well, either you run out of compute. Usually I would probably set these kind of jobs up in such a way that I set a certain war clock time, and at some point the job will run out of war clock time, and I will just use all of the candidates that it has managed to evaluate. In the meantime, you could also set, well, every worker has to create so many generations. One thing I have not mentioned yet is that, of course, at some point you have to receive incoming individuals from the other workers. So you can see after the first generation, one hasn't arrived. One has just arrived previously. So it checks at this point, but nothing has arrived yet. So when it checks again after this generation, so just after the third population, that is after before the third gray box, you can see there's an individual arriving, and it will just accept that and integrate that into its own population for future breeding. And essentially, the other worker is doing the exact same thing in parallel. I guess what I would say here is that I think lots of people, they kind of they focus a lot on the best algorithm to perform these kinds of things. I think so search is a kind of very old field in mathematics already, and I don't think I have much to contribute there. I think I'm much more interested in solving these technical problems, these communication and parallelization and scaling problems, because I think if you look at Optuna and at all of these other, or lots of these other tools, they are much more focused on cloud, because I guess that's where most of the users are. But since we are all here working on Leonardo, then maybe a tool that works really well in an HPC context, that's kind of more interesting for me, at least. Right, that brings us to our next exercise. So again, it's a sort of it's a basic example. We are still using just our very, very, very basic MNIST training, but now we'll use just populate instead of Optuna or random search. So you'll need
Oskar, sorry for interrupting. Sorry, there is
Go
one
ahead.
question in Discord from Konrad.
Yeah,
If we can
I saw that.
Yeah. Okay.
I can read. So there was the question: in case of opportunity, the decision is made synchronously for each node after gathering results? Question mark. I don't think so. So there is no sort of synchronization step, but there is this. They all use this database. So you called this suggest, or these suggest methods. They are still executed, as far as I know, on the worker node. So in that sense, it is also asynchronous. Like the workers don't they exchange information, but they all do it via this database. And well, that might be a bottleneck at some point, but there is no sort of explicit synchronization barrier that is sort of imposed on you by the algorithm, as far as I know. I hope that answers the question. But I still think this is kind of useful to talk about, because for a lot of these population-based algorithms, or oftentimes also for, there are sort of different kinds of trade-offs. I mentioned when I talked about the parallelization of the Bayesian algorithm, that you need to think about how you are enabling parallelism. So in the evolutionary or population-based algorithms, it is often kind of trivial to parallelize them. You just have, you have an entire population that you can evaluate independently of each other. But then if they all take different amounts of time to evaluate, then you might have to think about how to get around this synchronization barrier. And then on the other hand, for these Bayesian optimizers, like the basic form of them, they will only give you a single candidate, and then that's also difficult. You would also have to think about how you parallelize that. You have to make sure, okay, I need actually many I need to generate many candidates in parallel, and then so I can do meaningful work with all of the resources that I have. Yeah, I hope that helps. Right. So yeah, then to the exercise. So again, there you might spot some similarities to what you had to do for Optuna there, but there are also some differences. So in here, you have to define some kind of loss function that we're using. One difference that might be important immediately is that Populate, it always is minimization. So we always think of it as a loss. So if you are using an accuracy, for example, you might want to return the negative accuracy. So if you're using, you could use like there's many metrics you might want to use as the metrics to optimize for your in your hyperparameter search. You could also just use loss, then you don't need to do anything. But if you wanted to use, for example, your validation accuracy, then you would need to have something where lower is better. Yeah, and then so this params data structure is in some sense similar to this. I think it's called a trial in Optuna, except it's basically just a dictionary. So it contains all of the parameters that you gave when you defined the search limits that you for the search that you wanted to explore. So you have, for example, here batch size, for example, and then the min and the max that you want, and then you just have here params batch size, and that gives you the value that Populate would suggest you explore next. Yeah, and it's this dictionary. It's not quite a dictionary; it has some more things in it, but you can use it as think of it as a dictionary for now that just contains all of those parameters. Well, like yeah, the value is always the key. There's always the key value pair. The key is just the name of the parameter that you gave it, and the value is then the value that this current candidate has. Yeah, I already talked about the limits, so you at some point have to decide limits. In Optuna, you gave it when you sort of did the sampling itself. Here, you kind of do that in advance. And then this propagator I mentioned earlier, the default one is this genetic or evolutionary optimizer. This is what the default one will get you. You will need to give it a population size. That basically just means until it reaches or until it has enough candidates evaluated to fill a population, it will do a random search until then. So that's just means essentially that the first like it will randomly generate a population, and it will then use all of these evolutionary operators to improve that population over the generations. Yeah, it needs the limits, and I believe you don't really need a random number generator, but if you want to initialize it with for example, the rank of the worker that you're on, then you can do that. I think otherwise it gets initialized in some other way that you don't really need to worry about. But yeah, if you wanted to explicitly initialize it, then you can do that. And then the populator, this populator object, that is the thing that performs all of the communication, and it invokes this propagator that you already defined. So it will need this the loss that it's supposed to optimize. It will need a propagator, and then I think also again the rest of them, these parameters are just sort of they are optional. You don't need them. I think that you might want to give it some like sensible number of generations, so you don't have to train a bunch. Yeah, and then you basically this is the version of Optuna like trial.optimize. You just let the populator populate, and yeah, that's all you have to do. Yeah, so there was another question whether I could share the presentation. Yes, I will add the presentation to the repository. I was just still working on it today earlier. That's why I haven't edited it yet, but I will do that after we're done here. Yeah. Okay, then let's be back at 60. Well, I guess for European time, 35 minutes after 3. And yeah, again, if there's any questions in the meantime, then also, yeah, if you feel like these exercises are too hard or too easy or don't take the correct amount of time, then yeah, feel free to comment about that, because yeah, I don't have a sense for that. Yeah, good luck. Yeah. So again, this was a kind of fairly, basic example of what you can do with Populate. There are some more advanced features. So the first one would be island models. So then, since this is a multi-GPU training, what you can also do with Populate is that you have multiple ranks that perform, like that contribute to a single candidate evaluation. That means you can do things like at least data parallel. So for data parallel, we have an example. I can, if there's interest and time, I could also try and demonstrate that. But yeah, in principle, you could also implement a model parallel evaluation. Then we have also pruning that works a little bit differently. What we do is that as you generate like losses over like evaluations, you can we try to predict what the final loss will end up being, and then yeah, if we predict that the final loss will, or the final sort of performance will not be very good, then that individual can also be abandoned before it's fully, like before the training is fully complete. So it's a similar idea as to what, for example, Optuna does, but yeah. And that's also, so there was before, so yesterday there was a question about some compatibility issues with Populate. The library that we're using to do this this modeling, that is the one that's apparently not very well maintained anymore. So it causes some issues. So we'll probably replace that as soon as possible. So we can use like Python 3.13 and so on. And of course, yeah, we also implement some other algorithms. But yeah, I guess that's, as I mentioned, that's not really what I'm the most excited, like the most exciting thing for me. I'm more interested in all of the infrastructure bits. Yeah, so I mentioned islands. So what does that mean? So right now, the workers that you created, they would just, whenever they had finished evaluating an individual, they would send the results off to all of the other workers. And so they can use them in their own to generate their own future population. Well, there's two reasons why you might not want to do this just like that. So the first one is if there's a reason you want to limit communication, then you could say, well, we don't really need to communicate everybody or everything. We can just communicate the most relevant parts of information. So you would then only you could then sort of have different islands, and within one island you do the same thing as before. So every worker sends every information it has to all the other workers immediately. But then between islands, you only exchange information every now and then. So you could imagine, for example, that you have several nodes, and the connection between nodes is way weaker than the connection within a node. And then you could, for example, have one island on each node. But yeah, well, if you have a strong network, that might not be particularly important to you. There's another reason, and that's just for optimization purposes. So let's say your optimization sort of gets stuck in a local minimum. But if you can isolate that to just one island, then you could sort of by exchanging, by sort of loosely coupling the islands together, you maybe sort of not trap all of the islands in that local minimum, and then by occasional exchange, you could maybe try and free the stuck island. Yeah, that's kind of the optimization angle of why islands might be useful. I wanted to mention something else, but I forgot. Oh yeah, another thing is that's not currently implemented. That was just an idea I had. It might be interesting to have different optimization algorithms running on each island. But yeah, I have never tried that. That's just an idea that I want to try out at some point. That yeah might be interesting. Because then again, right now you have to choose from all of the myriads of different optimization algorithms, and if you just run all of them at the same time, then you don't have to think about that anymore either. Good. Yeah, so much on islands. Then I guess, yeah, this is maybe more interesting in this context specifically, these multi-rank workers. So what that means, for example, is that you can use multiple GPUs for each worker relatively conveniently. So you can just give the island. So, well, I wrote islands here. The populator class that you used before, you can basically just exchange that with the island. The island is just kind of a wrapper around the populator. So yeah, they should both take that parameter, and you could set that to some value that's greater than 1 if you wanted to use, for example, DDP. And then you have to slightly change the loss function of your sorry, the signature of your loss function, because it now also takes an MPI communicator object, or rather an MPI for pi communicator. Yeah, you can use that inside of the inside of your optimization or in your loss computation in order to do, well, pretty much whatever you want, any kind of communication you want to do within that like within that kind of group of processes or ranks that are working on the same evaluation of the same individual. And then, so for example, PyTorch GDP specifically, you then have to just set up the process group just as you have, I believe, before on one of the previous days, and then wrap the model and the data loaders with DDP, such as you have done before. And that's all you need to do. And yeah, everything works as before, except now we have kind of different communicators going on in parallel, or we have sort of a hierarchy of communicators where we have some sort of only like in this communicator that is working on the same, that are kind of representing the same worker. Only the rank 0 of that one will that will kind of do all of the communication that is relevant for populate, and the other ones, they will just contribute to the actual, like to the evaluation. Yeah, I think that's what I wanted to say on that. So yeah, there's lots of things I didn't talk about. So in the sort of context on how to automatically, like of AutoML, like how to find better models, how to find better architectures, how to find better optimization schemes. There are some other things to mention. That's so you could, for example, get a reinforcement learned agent that helps you out with these things. If you, yeah, that's kind of let's say an established kind of branch of that tree in research and literature. There's also more broadly this idea of meta learning, so learning to learn, where there's lots of interesting material that yeah you might want to explore. And then there is this. It's also by now it's quite old, I think, at least in machine learning age. Was this old paper on neural architecture search without training. So what they do is they basically generate an architecture, and they try to evaluate that architecture without training it at all. Which could also be interesting in this context. You can basically slot that in to all of these optimization tools and algorithms, but you just don't do any training. You just do what they are doing. So if you would find that interesting, then yeah, you should look for this NASWAT. Yeah, but that's all I have prepared. We still have some time. I think originally we were going for 15 more minutes. So yeah, if that is interesting, I could try and demo like PyTorch DDP, or yeah, or we could finish whatever you would prefer. I'm not sure.
I want to go for demo, but if somebody else wants to add, sure.
Yes, yeah, I can have a have a go at the demo. So let's just check here. So I already put in this DDP worker example, but I'm not sure whether that works out of the box. We can just, of course, try. So yeah, let's just try and see what happens, because oh, interesting. Maybe did I do? I'm not allowed to have that many CPUs. What is the? No, count per node can be set. Wait, I did. Did I use the old? Yeah, I assumed probably 8 GPUs per node because I'm used to other machines. But of course, we only have 4. Let's go back to 8 CPUs. Let's try that. There you go. So that's at least that. Now it's just pending. So let's look at the script in the meantime. Okay, there are some things that won't work. For example, so I think this script is used to be run on other machines, and I'm not sure whether on Leonardo these Slurm environment variables are set, but we can, of course, just hard code it. So for and let's go 8. There might be more relevant or like more elegant ways to do that on Leonardo, probably. Let's have some fewer initialization. Yeah. Okay, so right now we are going for 4 GPUs. I said we're having 2. I asked for 2 nodes. I had a slightly larger parameter space that we are searching for. And then, I guess, this is also a convolutional network and not the exact same example that I used in the exercises. Then what you need to do is, I think this is probably quite similar to the earlier DDP. You need to initialize this process group somehow. But I guess this is so. Yeah, exactly. You need to set the address and the port, but this should be. This should work like this. So you get some more information from the environment variables that you extract from there, and then you need to. So we are using this method. So we are using this TCP store that takes the address and the port and like the sizes and these kinds of things. So yeah, we'll see whether it works once I've gone through this. There are some other there's these other Torch provides like several methods to do this, but I guess so this is whether it was the default that we are going with because, well, we have Slurm, yeah, so that should be fine. And what we are also making sure is that we on each rank we have to make sure that we we are using the correct device. There might be an issue sometimes where if you're so I'm right now assuming that every rank can see all of the GPUs. If the cluster is configured differently, it might be that each rank, for example, could only see 1 GPU anyway. Then this part of the code would change slightly. And yeah, then I had then you of course need to. I mentioned this. You need to wrap your model into this distributed data parallel, and you need to in the here. So the data loaders that you are using here, they need to also be wrapped, do they not? So we do that, and there we go. Yeah. So yeah, we are here getting these distributed samplers instead of the normal, or like wrapping them around the data sets in this case. Yeah. So let's see. Job started. It probably crashed. That looks good. Right. Yes. So I mentioned that I use MLflow as visualization. So of course, I did not prepare for that here. So let's remove MLflow from our script. I think all of this can just go. Okay. Maybe I should start using the reservation. Now it's running. I'm wondering whether there's any output. There we go. I'm probably downloading data. I shouldn't be doing that. Yeah, so in this example script, I just had it to be sort of convenient. I first downloaded the data, but of course we do not need that here. Wait, did I set the... Yeah, it uses the one that is already downloaded too fast, but so that shouldn't be a problem. Mhm. Okay, now it seems to start working. Yeah. Loss looks a little bit suspicious, but Into one more epoch. So yeah, you can see it runs stuff, and should maybe this right now you can't see much more than that it runs, but yeah, of course, for this example, DDP is not entirely, like, it won't get you any speed up or anything, I don't think, because it's too small. But yeah, just to demonstrate the principle. Okay. I think, yeah, that's pretty much what I've got.